We are all here to celebrate this RIDC Research, Innovation and Dissemination Center for Neuromathematics, RIDC NeuroMat, or CEPID NeuroMat in Portuguese, which is due to finish next month. And we'll open this celebration, this special workshop, the closing workshop of NeuroMat now with this welcome session. So the other speakers will be Roberto Marcondes first, representing the Institute of Mathematics and Statistics, which is hosting this event. Then with Professor Luis Nunes de Oliveira, remotely, who will speak on behalf of FAPESP, the São Paulo Research Foundation, which is the funder of this, the main supporter of the supporter of this center. And then Professor Osvaldo Bafa, who is the director of the center, will give the final speech of this welcome ceremony. And then at 9:10 Brazilian time, we'll have the first scientific talk by Eva Locheba, who is in France. So let's... this initial ceremony will be in Portuguese, as agreed. So yeah, we apologize for that, but so the talk will be in Portuguese. Roberto Marcondes, Luis Nunes, and Osvaldo Bafa will speak in Portuguese. And then the rest will be in English, okay? Okay, so Roberto Marcondes, you can start. Qualquer lugar.
Talvez eu tenha que aparecer aqui. Tô aparecendo. Bom dia. Vai lá na frente? Tá bom. Então tá bem. Aqui aparece? Então tá bem. Então, bom dia a todas, bom dia a todos. Bonjour, Eva. Bem-vindas, bem-vindos. Meu nome é Roberto Marcondes, eu sou professor aqui no Departamento de Ciência de Computação, aqui do IME, USP. Bom ver amigos, conhecer pessoas novos amigos, novas amigas, encontrar velhos amigos como o Luiz. Bom te ver, Luiz. Faz tempo que a gente não se encontra pessoalmente. Eu sou professor aqui no Departamento de Ciência de Computação, aqui no IME. Estou diretor do IME, né, do Instituto de Matemática, Estatística e Ciência de Computação, desde o dia 2 de abril, junto com a Florência, que é também uma das líderes aí do NeuroMat e também é vice-diretora do IME. A gente começou dia 2, porque se a gente começasse dia 1º de abril, ninguém ia acreditar. É um prazer enorme, pessoalmente, então, participar dessa cerimônia com algumas poucas palavras, representando o IME, mas também alguém que já teve chapéu da FAPESP e que acompanhou o NeuroMat por um bom tempo, de 2013 a 2023, para ser preciso. Então eu vi grande parte da construção do que aconteceu com o NeuroMat, trabalhei muito próximo com o chapéu da FAPESP, com o Antônio, né? Então é bom ver agora em perspectiva tudo que foi construído nesses anos todos. Então dá orgulho quando a gente supera as dificuldades naturais que acontecem, vai acreditando com propósito e vê o que aconteceu em relação a isso. O IME, em particular, ele deve muito a tudo que foi construído nesse trabalho do NeuroMat. O NeuroMat foi o maior projeto de pesquisa que existiu no IME na época que ele apareceu. Depois várias outras coisas começaram a florescer em relação à pesquisa, em particular, financiada pela FAPESP, financiada por outras agências de fomento. Mas o NeuroMat ele foi pioneiro em relação a isso. Então, para nós, o NeuroMat tem um significado muito especial. Essa questão da pesquisa interdisciplinar, envolvendo probabilidade, estatística, computação. Estou vendo a Kelly aqui, vários pesquisadores do Departamento de Ciência de Computação, em particular, que estiveram presentes desde o começo da criação do NeuroMat. Então, essa parte interdisciplinar, essa parte da pesquisa em si, de modelagem, usando estatística aplicado à neurociência, tem cumprido um papel super fundamental em tudo que a gente faz. A infraestrutura física aqui, a infraestrutura de pessoas, todas as contribuições especiais, especialmente em relação à difusão, à disseminação, quer dizer, fazer chegar a informação junto à sociedade do que a gente faz. A gente sabe que o NeuroMat cumpriu um papel, cumpriu e cumpre um papel super importante. Não preciso lembrar vocês todos as questões da atuação, por exemplo, em relação à Wikipedia, redes sociais, construção de mensagens importantes para comunicar à sociedade as coisas que a gente faz. Então, é uma quantidade gigantesca de coisas que o NeuroMat construiu ao longo desses anos todos, e eu queria deixar registrado em nome do IME o agradecimento do Instituto, o reconhecimento do Instituto, porque isso realmente ajudou a construir essa imagem da atuação do Instituto junto à sociedade, que é super fundamental, fora a parte de pesquisa mesmo que vocês fazem super bem. Deixa eu dizer um pouco sobre o IME e a importância, então, do NeuroMat, principalmente para os nossos colegas que não são do Instituto. O IME, ele tem um papel super importante na universidade, no sentido que nós somos o Instituto de Matemática, Estatística e Ciência de Computação do campus do Butantã. Então, para vocês entenderem um pouco o que significa isso em tamanho, nós somos 170 docentes, mais ou menos, no IME, mais uns 90 funcionários. Então, tem 260 pessoas. Cabe num auditório de tamanho médio aí, 260 pessoas. Se você somar alunos de graduação e de pós-graduação, então são pessoas que ao longo dos anos do NeuroMat estiveram expostos às mensagens do NeuroMat, a gente está falando de 1.500 alunos de graduação, 800 de pós-graduação. Mais uns 60 pós-doutorandos, muitos pós-doutorandos passaram e passam pelo NeuroMat. Então o IME é uma comunidade de 2.600 pessoas, mais ou menos. Então, já não é mais tão pouquinho. Eu comecei falando que a gente cabia num auditório, mas quando você pensa em 2.600 pessoas que compartilham a propriedade comum de gostar de matemática, já virou uma coisa diferente. Mas, além disso, o IME é responsável por ensinar matemática, estatística e computação no campus do Butantã. O que significa isso? Significa que não tem uma pessoa formada em, para pegar um tópico da moda, STEM. Então, Science, Technology, Engineering and Math. Não tem um profissional formado em STEM no campus do Butantã que não tenha aprendido matemática, estatística e computação com a gente. Então, a gente está falando aí a gente já está falando de dezenas de milhares de pessoas. São 25 mil matrículas por ano. Então, o tipo de mensagem que a gente constrói em centros, por exemplo, desse, tem uma capilaridade, eu costumo brincar, que movimenta PIB. Então, porque tem engenheiro, tem físico, tem economista, tem gente de astronomia, tem essas coisas todas. Então, esse tipo de construção que vocês fizeram em relação ao NeuroMat aumenta o nosso orgulho, porque a gente começa a perceber o impacto do que a gente faz aqui, e grande parte se passa aqui, porque o NeuroMat, além de ter essa infraestrutura que serve para vocês, gentilmente, tem várias coisas que acontecem aqui, por exemplo, aqui nesse auditório e em outros andares. Então, eu vou concluir dizendo, em nome do IME, dado que esse que é o chapéu que vocês me convidaram para participar, que o IME agradece enormemente isso que vocês construíram, e a gente está muito curioso e pronto para apoiar para os próximos 10, 15 anos do que vem aí pela frente. Tá bom? Eu vou parar por aqui. Obrigado, gente.
Obrigado. Agora vamos dar sequência às falas com a fala do professor Luiz Nunes, representando a FAPESP. Fica à vontade, Luiz.
Tá bom. Muito bom dia a todos. Eu gostaria muito de estar aí em São Paulo, mas eu sou em São Carlos, agora sou do IFISC, e eu tenho que dar aula hoje à tarde. Seria impossível eu estar aí agora e depois voltar para São Carlos em tempo. Então, o Bafa me fez o favor de permitir que eu falasse por vídeo. E, para mim, é uma grande satisfação. Eu gostaria, primeiro, de fazer uma pequena homenagem à memória do professor Galves, que era uma pessoa, como vocês sabem, extraordinária no sentido literal da palavra. Eu conheci na época em que ele estava querendo submeter o projeto para o primeiro CEPID, lá por volta de 1998, 99. E nós tivemos muitas conversas depois, quando o CEPID começou, que tinha uma perspectiva bem diferente do NeuroMat, mas foram sempre conversas memoráveis, né? Ele estava sempre cheio de ideias, ele defendia tenazmente as suas ideias, tinha opinião sobre tudo e tinha muito entusiasmo. Toda vez que conversei com ele, eu aprendi alguma coisa e eu me lembro muito bem de várias dessas ocasiões. Nós falamos de física, política universitária, de como devia funcionar um CEPID. Uma vez eu dei uma entrevista para um jornal e, num certo ponto, a entrevistadora me pediu um exemplo de um projeto de matemática que tivesse repercussão na área de humanidades. Mas ela, logo em seguida, falou alguma outra coisa e a conversa desviou. Bom, quando saiu publicada essa entrevista, no dia seguinte, o Galves entrou na minha sala e ele veio reclamar. E ele disse assim, olha, a jornalista pôs a bola na marca do pênalti para você falar de um trabalho que nós fazemos e você chutou fora. Eu tive que reconhecer que era verdade. Mas isso daí fazia parte do jogo em que a gente estava envolvido. O Galves era uma pessoa muito interessante, ele incomodava muita gente, e era fácil encontrar quem não gostasse dele. Entretanto, ele tinha uma postura e um dinamismo que personificava o espírito universitário, acho melhor do que qualquer outra pessoa que eu conheci. Então, ele deixou uma lacuna que a USP vai ter dificuldade para preencher. Já no CEPID, a história é outra. E porque vocês souberam reconstruir o projeto. Teve pouco tempo, mas já tem evidências claras que conseguiram reconstruir. É mais ou menos inevitável, quando se fala nisso, pensar na história da Fênix. Mas eu quero fazer referência a uma outra imagem. Quem leu o Ana Karenina sabe que o Tolstói começa dizendo que as famílias felizes são todas iguais, enquanto que as infelizes, cada uma é infeliz à sua maneira. Com os CEPIDs acontece o contrário. Os projetos mal sucedidos são todos iguais. E o traço comum é que falta sinergia. O trabalho acaba virando um conjunto de subprojetos independentes e as subequipes não conversam entre si. O NeuroMat fugiu dessa rota. No começo, com o impulso do Galves, e depois, com o falecimento dele, isso ficou muito claro no que foi feito pelo Bafa e pela Florência. Eu tive a oportunidade de acompanhar só nesse último ano, né, porque eu peguei esse chapéu de que o Roberto falou e assumi papel na coordenação do CEPID em abril do ano passado. Então, só nesse tempo que eu pude acompanhar o projeto, mas o que eu vejo é que ele tem um dinamismo que não é muito fácil encontrar entre os CEPIDs. Em particular, eu fiquei muito impressionado com o número de workshops que foram promovidos, tanto para a comunidade interna como para a comunidade externa, e aí o NeuroMat tem um papel muito importante, como o Roberto já comentou, né? Então não vou me demorar nesse ponto. Então, de certa maneira, eu vejo que esse evento é icônico, porque ele mostra que vocês seguiram uma trilha que é diametralmente oposta ao caminho do insucesso. Né? E aí eu vou me dirigir ao professor Bafa e à professora Florência para cumprimentá-los por essa escolha e por tudo que foi feito nesse tempo principalmente nesses últimos anos em que vocês assumiram a liderança do projeto. Né? Quando o programa CEPID foi lançado, lá em 1999, 2000, o governador Mário Covas veio à FAPESP para falar na cerimônia de lançamento, que foi feita no auditório da FAPESP, estava totalmente lotado, e ele falou sobre os méritos desse programa. Né? Ele estava muito impressionado com essa possibilidade de interagir com a sociedade, com a possibilidade de gerar produtos de inovação, e ele não escondeu esse entusiasmo que ele tinha. Ao contrário, ele falou e disse que se a FAPESP continuasse nessa linha, ele ia até tentar aumentar a verba da FAPESP, dobrar a verba da FAPESP, que já tinha sido incrementada de 0,5% do ICMS para 1%, então, recentemente. Ele prometeu que até tentaria aumentar esse percentual. Pois bem, isso foi há 25, 26 anos. Hoje em dia, nós temos uma perspectiva diferente. Eu tenho certeza de que, se o governador estivesse aqui hoje, ele estaria orgulhoso do trabalho que vocês têm feito. Então, com isso, eu vou encerrar, cumprimentando o professor Bafa, Florência, o Roberto. Como ele me disse, faz muito tempo que a gente não se vê em pessoa, então, pelo menos em 2 dimensões, foi interessante ter tido essa oportunidade. Então, agradeço e volto a cumprimentá-la pelo trabalho.
Dando sequência agora, o professor Bafa, encerrando a sessão.
Dá para pegar aqui, não? Bem, bom dia a todos. Eu queria inicialmente agradecer a presença, cumprimentar o professor Marcondes e a professora Florência, que iniciam a gestão da diretoria do IME, desejar sucesso, que seja uma gestão profícua, que o Instituto continue na mesma trilha que vem seguindo ao longo dos anos, né? Sempre um ciclo virtuoso. Agradecer as palavras do professor Luiz, que é um dos coordenadores do programa CEPID na FAPESP. Eu tive a honra de ser aluno do Luiz e aprender um pouco com ele, né? Ele se esforçou muito, mas, enfim, foi o que eu pude aprender. Eu escrevi um texto aqui que eu acho que fica mais sintético, porque senão eu vou ser afetado pela emoção aqui. Então eu vou ler, que acho que sintetiza o que eu penso nesse momento. E a história é o seguinte, né? Em 2012, um grupo de pesquisadores, liderado pelo professor Antônio Galves, concebeu uma iniciativa ambiciosa: desenvolver novas ferramentas matemáticas para estudar o cérebro. A proposta foi apresentada à FAPESP com um CEPID, um Centro de Pesquisa, Inovação e Difusão, e teve início em 2013. A primeira vez que eu ouvi falar desse projeto foi em 2017, em um seminário que o Galves apresentou no Instituto de Estudos Avançados, lá em Ribeirão Preto. E eu confesso que tive, naquele momento, dificuldade em compreender o que seria essa nova matemática que o projeto buscava construir, né? Era assim que ele vendia a ideia. É uma nova matemática, uma nova matemática. Naquela época tinha aparecido essa história de fractais, né? De wavelets. Falei, será que é algo assim, uma nova transformada? O que é isso, né? Bom, depois do seminário, o Galves visitou o nosso laboratório, viu o que a gente fazia lá, e por sugestão da Cláudia, eu acho, né? Ele nos convidou a integrar o projeto. Então, a partir de novas conversas, da participação em seminários e diferentes eventos do NeuroMat, o nosso grupo passou a se desenvolver mais direto em suas atividades. Aos poucos, nós compreendemos que o projeto precisava de dados neurofisiológicos precisos para testar seus modelos e demonstrar o comportamento estatístico do cérebro em funcionamento. Ficou claro, então, que o NeuroMat buscava uma interação dialética entre teoria, matemática e experimentos quantitativos em neurociências. Esses dados não poderiam simplesmente ser extraídos de bancos de dados ou de repositórios existentes, pois exigiam experimentos desenhados especificamente para esse fim. Naquele momento, estávamos começando a desenvolver um software de neuronavegação e sonhávamos com o uso da robótica associada à estimulação magnética transcraniana. Bingo! Estávamos no lugar certo, no momento certo. A cooperação foi intensa e teremos oportunidade de relatar em uma das apresentações deste evento parte do que conseguimos realizar juntos. Ao longo desses 13 anos, muita coisa aconteceu. Celebramos muitas conquistas, mas também enfrentamos perdas importantes. 5 de nossos colegas faleceram: Ernest Hamburger, Gubi, Galves, Gabriel e, mais recentemente, o Puzar. Alguns participantes da primeira fase seguiram outros caminhos, outros se juntaram ao grupo. Assim é a vida. Ela se transforma, se reorganiza e segue adiante. Ao analisarmos nossos arquivos, constatamos a dimensão do caminho percorrido. Participaram do NeuroMat 20 pesquisadores sêniores, 17 pesquisadores associados do Estado de São Paulo, 10 pesquisadores de outros estados, 30 pós-doutorandos, 51 doutorandos, 26 mestrandos, 21 técnicos foram treinados, tivemos 26 bolsistas de jornalismo científico e 19 bolsas de iniciação científica. São recursos humanos preciosos formados ao longo desses 13 anos que certamente continuarão fazendo diferença onde quer que estejam atuando. Este é, sem dúvida, um momento agridoce. O projeto se encerra e isso nos entristece. Por outro lado, deixa frutos importantes. Podemos dizer que o CEPID se ramificou em vários centros. 3 institutos nacionais de ciências e tecnologias, INCTs, apoiados pelo CNPq e por fundações de amparo à pesquisa estaduais, além de um centro de pesquisa, inovação e extensão CEPIX, sediado no IME, nasceram dessa iniciativa. São frutos desse projeto. Pessoas que foram formadas aqui puderam alavancar nossas iniciativas. Eu diria que a árvore de contexto, que é uma coisa muito comum, muito cara entre nós, né? Ela cresceu e se ramificou, ao contrário do que a gente faz nas novas pesquisas, que é sempre encontrar a menor árvore, né? Foi o contrário que aconteceu aqui. Bom, então a gente formou aí um número expressivo de mestres, doutores, pós-doutores, divulgadores de ciências e técnicos. Também foi produzido e divulgado em revistas internacionais e outras mídias uma quantidade significativa de conhecimento. O NeuroMat tornou-se ainda um importante colaborador da Wikipedia, como já mencionou o Marcondes, na área de matemática, contribuindo para a difusão e o acesso público ao conhecimento nessa área. Mais importante ainda, o CEPID criou uma comunidade interdisciplinar sólida e motivada, que continuará colaborando nos próximos anos em torno de um projeto de longo curso e de grande desafio. Ao fazê-lo, honra o trabalho pioneiro e a liderança do seu fundador, o professor Antônio Galves. Então, com essas palavras, eu queria encerrar minha fala, agradecer a presença de todos, desejar um workshop que seja produtivo, que a gente saia daqui com mais ideias, mais colaborações e mais trabalho para fazer. Muito obrigado.
Bom, obrigado a todos e todas por essa sessão. Acho que então está aberta, né, a nossa cerimônia, né, o nosso evento de encerramento do NeuroMat. E eu vou agora mudar para o inglês, né, que é a língua oficial do resto. E agradeço então a participação do professor Roberto Marcondes, do professor Luiz Nunes de Oliveira e do professor Bafa. Claro, eu sei que vocês são pessoas muito ocupadas e então devem ter compromissos, não é obrigatório ficar. Tá? Agradeço mais uma vez. So let's go back to English, and according to our schedule, we'll start at 9:10. So we still have 10 minutes, 12 minutes to go. So there'll be a short break because we have to respect time. You know, we're very punctual here in Brazil, so we'll respect time, and so we'll start at 9:10 punctually with Eva Locheba. Okay, so you have 12 minutes to rest.
Je vais essayer si je peux partager l'écran. Tu le vois, Guillaume?
Oui, je le vois.
OK, alors j'arrête. Comme ça, on peut faire une pause aussi.
Ouais. Et donc, tu es déjà en vacances ou pas encore?
Non, je ne suis pas en vacances, mais cette semaine, je ne vais pas à la fac, il fait trop chaud. Mon bureau, il est sous le toit, c'est insupportable.
Ouais.
Donc là, je suis à la maison.
D'accord. Ouais. Ouais, non, mais je pense que j'ai lu un extrait qui disait qu'il faisait très chaud en France.
Oui.
Mais bon, ça commence à être la vie normale, non? Enfin, quelque chose qui
Ouais.
arrive.
Okay, thank you very much for the presence in this closing workshop of the NeuroMat project. So we are going to begin now with a thematic session about stochastic neuronal networks, and it's very nice to see here many friends that we did during all these years of the project, and to see them talking to us about the developments they did in these years. So our first speaker is Eva Logerbach from École Polytechnique in France. She's a long time friend of us, and she collaborated a lot, and she participated in all the activities of the NeuroMat project since the beginning, and working jointly with Antonio for many years. So Eva, it's a pleasure to introduce you in this session, and she's going to talk about the mon French is maybe you can talk your title. Okay. Yeah. Thank you very much, Eva.
Thank you, Florencia. I don't see you anymore because I put it full screen. So do you see my slides? I guess yes.
Yes, no? Yes, we can see this.
So I decided for this title, so I will read it. 2 ou 3 choses que je sais d'elle. 13 years of modeling spiking neurons with stochastic point processes having memory of variable length. And I chose this title because in 2007, when I first met Antonio, he gave a talk in one of the French probability conferences, and he started with this 2 ou 3 choses que je sais d'elle, which is actually the title of a movie, which he liked very much. And then after that, he was speaking about chains having memory of variable length, which is one of the research themes that he was working on at that time. So it is to remember this event when I first met him and when we started discussing. So Antonio, Rocky, and Claudia have asked me to give an overview talk. And so I will try to give you an overview of what I think what we did partly on these stochastic spiking neuron models since the last 13 years that we have been working on that in NeuroMat. So in my talk, I will discuss these point process models for big systems of spiking neurons. I will recall you, most of you know, because you have already seen a lot of talks by us about this, that we will model them as point processes with memory of variable length. And so I will give the big part of the talk is an overview of some of the research activities that we had in NeuroMat, and then I will finish with some open research directions. And of course, most of what I'm going to talk about, I have learned it from Antonio, which you see here. This was the IHP trimester, and from Christophe Pouzat. And it all somehow started exactly 13 years ago when we wrote the first paper with Antonio, which is called a system models to model spiking neurons. So I will try in my talk to convince you that these point process models are good models to model the neurons, that we can use them to explain collective limit behaviors, like oscillations and neural field equations, and also to deal with long-time behavior and with memory. And this is some advertising, but I will come back to that later. As you all know, we also wrote a nice book with Antonio and Christophe, and a lot of things about these models are written in there, actually, and in a rather accessible way. Okay, so the data we are interested in.
Eva, yes, we are seeing now in a Google tab. Maybe you click something.
What do you see?
Oh, it's here. It's here. Sorry. We are not seeing your slides anymore. Now, okay. It's okay. So sorry, you can continue.
So what do you see? Do you see now the overview thing and with the photo of Antonio and of Christophe?
What? Yes, we are seeing. Yes.
Okay. I don't hear you, but okay.
Yes, we are seeing your slides now, but are not in full screen maybe. I don't know if before.
That's strange.
No, it's smaller now. Maybe you can click in presentation mode or something like this. Now
I did it in presentation mode. I can try to do it.
We are not seeing the slides.
Yeah, because I stopped it.
Okay.
Now you see the slides, but they are small.
Yeah, this is, but in the application, maybe you can put presentation mode in the application, in the PDF reader.
Yeah, that's what I did before. That's why I didn't see you. So this is full screen for me.
Okay. It's okay, like this.
Yeah.
Okay. Yeah. Thank you. Sorry for that.
No, I should have come. I apologize, but it was not really possible. So, overview of the talk. So, should I talk about all this? No, okay, I start here. So, do you see the raster plot of Christophe here on the slide?
Yeah.
Yeah, okay. So, we are interested in these spike trains. So, here you have an example that I got from Christophe where we see the subsequent spiking times of 3 neurons over time. So the time is downstairs and we have neuron 1, 2, and 3. These data, Christophe got them after spike sorting. You all know that this is difficult and not so evident, but anyhow, so once you have them, we are dealing with these data, which are point process data, because we just say at which exact time a given neuron has emitted a spike. And so in the models that we have, we reduce neurons to points. So we do not take into account any spatial structure and we do not speak about axonal transport or other things. So as I said, each neuron is represented by the temporal succession of its spiking times, and which for mathematicians is nothing else than saying that we are dealing with point processes, and the ones we use, people call them multivariate Hawkes type processes. So multivariate is because we have tons of neurons, so we have different neurons, and so to each neuron is associated its own spiking point process. And I say it's a Hawkes type process because we have this variable memory length. So some people in NeuroMat also call it the GL models. And the important features of the model are, well, that we represent, I'm sorry for the highlighting, so we represent each neuron actually by its membrane potential process, which accumulates the stimuli which come from its presynaptic neurons. And then there is spiking, which is random actually. It is at a given rate, which means that we have exponential clocks, but the intensity of the clock depends on the height of the accumulated potential. And when the neuron spikes, its potential goes back to 0. And at the same time, the other neurons, they gain or they lose, that depends if it's excitatory or inhibitory, some additional amount of potential. And this is the effect of the chemical synapses. Okay. So here is the slide for the mathematicians, because I will use this notation later. So in the talk, or in the remaining minutes that I have, I will consider systems which are made of n neurons, and n will tend to infinity. I call x their associated membrane potential processes. So it's x of the first neuron up to the nth one. And here is the spiking mechanism. So each neuron spikes with a rate that is a deterministic function f of its potential, which means that the probability of spiking within the next little time bin of length h, given the past and given the potentials of all the other neurons, is actually something like a Bernoulli random variable. It's a 0-1 event, and you accept it with the probability f of x times h. As h has to be small, such that this is actually a probability. And when it is I which spikes at a given time, then its potential is reset to 0. And at the same time, all other neurons receive an additional potential value, which is the synaptic weight of I on J. So we have an associated structure of an interaction graph. And here is a picture of that, is one of the pictures that Christoph made for the book, where we can actually follow the successive direct synaptic influences of one neurons on others. So if you start with number 26 here, it directly influences neuron 42, for example, followed by neuron 96, and so on. And you can also look on the smallest loop that we have, such that the information which is initially emitted by 26 goes back to its. Okay. Good. So that was about the spiking, and in between successive spike, we just modeled the potential by some deterministic flow to speak about the leakage. So usually we take some exponential loss. So it follows just a deterministic exponential decaying differential equation. We can take other drift functions. That is not so important. Okay. So this is what people call a stochastic integrate and fire model. So stochastic because spiking or not is a stochastic event. Integrate because each neuron's potential is summing up the influences of the presynaptic neurons. And fire because then it fires with a weight depending on the potential. And people around Lausanne school, around Wolfram Gerstner, also call this an escape weight model. Okay, so this is the model. There have been a lot of people working on that. I'm only citing mathematicians here, and I will not speak too much about that. So there is, on the one hand side, the people who use mean field models of integrate and fire diffusion models. That means that we take a stochastic differential equation driven by Brownian motion to model the potential membrane, the membrane potential of a neuron. There are a lot of people in southern France that have worked on that. And in the work we have done in NeuroMat, we basically work with these point process models, and that's what I'm going to speak about, of course, in the rest of the talk. Okay, so I will resume joint works with all these people. I'm not going to, I hope that you see my mouse. So you see I put in blue all the NeuroMat researchers with whom I had the chance to work on this. So there are Antonio, Alini, Guilherme, Christophe Pouzat, Dasha, and Katro, and all these others also. Okay, so I want, in the first part of the talk now of the mathematical part, I want to convince you that it is sometimes good to pass from this microstructure description where I describe each neuron, each single neuron, to a mesoscopic description. And this is basically because the number of neurons that I called n is just very big. And so it is not very, it's not analytically tractable to describe each one of the n neurons if you have 10 to the power 11 neurons, which is just a too big stochastic system. And this is one of the reasons that people started to work with mean field models, where instead of describing each single neuron, we describe statistics of populations, of big populations of neurons that all behave the same. And what does that mean, that they behave the same? That means, well, they all have the same way of reacting to incoming stimuli, which means that their rate functions are the same, and that the system is basically invariant under rotating, under permutating the coordinates. So that is maybe reasonable in some subsystems of the brain. And then we want to pass to some limits, so we want to zoom out. And we have to do that. If you want to do that, we have to do it at a scale such that each single synaptic interaction, which is modeled by the synaptic weight, tends to 0. And so this is what we do. So we take a synaptic weight that doesn't depend on the pair of neurons which is involved, because they are supposed to be all the same. And to get some meaningful limit, we have to take a renormalization in 1/n, where n is the system size. Okay, so each single synaptic interaction rate of a given neuron on all of its partners is given by a fixed constant W divided by n, and n will tend to infinity. So together with Anna De Masi, Antonio, Enrico Presutti, in the follow paper of the one that I cited before, we showed actually that in this case we have convergence to a limit equation which people call Makin-Vlasov type equation, and where we get a stochastic differential equation for the evolution over time of each neuron's potential, which is of this kind. The only thing that I'm not going to explain it, the only thing is the red term here, which tells us that the joint action of the synaptic transmissions of all the neurons on a fixed one, so we isolate a fixed single neuron and we just ask the question, what is the influence of the whole system on this neuron doing? And in the limit, this becomes a drift. So in the limit, we keep this W here and is multiplied by the expected mean spiking rate at the given time. So we have the expectation of the spiking rate of any neuron because they are all the same at time t. And this is why people call this a nonlinear process, because the evolution depends on the law of the process. So for people in mathematics, that's not so evident to deal with these kinds of equations. Okay, so this is the limit equation. So as n gets big, each neuron's potential is described by this limit equation, and we have rates of convergence, which is something which is classical, is 1 over square root of the system size. And usually this convergence works only on finite times, which means if you observe the spike trains of the system during some finite time interval, this approximation will be valid, while it will not be valid up to time infinity. Okay. These are simulations by Cadmo. So it's the pure Hawkes case. So if I say pure Hawkes, that just means that we do not put the reset. Okay, so it's the same model, but the potential is not reset to 0. And you see the convergence to the mean field limit on it. So on this simulation here, we see the trajectories of the potentials of 10 neurons, and the system size is 20. Here, we also have 10 neurons, but the system size is 200. And for 5,000 neurons, you see that there is a deterministic limit, actually, okay? And we can prove it. Okay, so now I just wanted to give you some overview of works that we have been doing around this idea of mean field limits. So we have big systems of neurons, we have some limit system, and then you can ask the question, what does the limit system tell you about the finite system of neurons? And for example, we have been able to prove that the limit system can help us explaining the appearance or the emergence of collective rhythmic behavior. And this is something we did some time ago with Susanne Dietlefsen. I started that when I was visiting her with Antonio. She has also been participating in a lot of NeuroMat events. So we looked on the mean field limits of these models. They were structured in several populations. Here it is 2 populations. The one is excitatory on the other, and the other is inhibitory on the first one. And what you see on the figure is a simulation of the limit intensity, and we also see the finite system intensities that somehow fluctuate around these limit intensities. So in green, I don't know if you see the colors, you see that we have limit intensities which have a rhythmic periodic behavior, and in dark it is the finite systems approximations. And I wanted to stress that these oscillations is not something that we put in the system, it really emerges in the limit. There's a typo, just by the interactions between all these neurons. And we also added delay in the transmission of the spikes. So this is one possible result we had. I wanted also to mention a paper that we wrote together when Aline and Guilherme were in Paris on the postdoc position, and we started working with Julien Chevalier. Maybe I have to be quick because it's already 9:30, but we succeeded to prove that our microscopic neuron spiking model under certain conditions converges to the neural field equation, which is a very classical equation in theoretical neuroscience, which had been introduced by Amari, Wilson, and Cohen in the 70s, who proposed this equation to have a deterministic description of neuronal activity, which is spatially structured, actually. So we took our model, but the neurons were attached to positions, and the interactions in between neurons that are close to the same positions do only depend on these positions. Okay, this is called a multi-type propagation of chaos. And we were able to prove really rigorously the convergence to the mean field, to the limit neural field equation. So maybe I just show you the simulations that Julien did at that time. So where you also see the convergence actually. So downstairs, it is the time, and upstairs, it is a part, a slice of the brain. So it's one-dimensional here. It's just to be able to do the pictures. So what you see over time is how the activity evolves. So red means there is a high spiking activity, spiking right, and blue means there's nothing. And so you see how this activity evolves spatially over time. And this is for 100 neurons. For 1,000 neurons, you see already that, well, there is something very regular which is popping up, and this is the neural field mean field limit, if you want, and this is for 5,000 neurons is almost the same. Okay. So I prepared a slide where we had the equation, but because time is running, I will skip this, because I wanted also to mention this paper here. So for the moment, I have only been working in models where the synaptic weights were fixed. It's W divided by N, or it was something depending on the space divided by N. And it's very easy in our model to add plasticity, and we did this in the paper together with Antonio, Enrico, and Christophe, where we studied models where the strength of the synapses changes over time, and that depends on the calcium concentration actually that we have close to the synapse at a given time. And in that paper, which was very nice, we observed the phase transition in the long time behavior of the model, and this is something we know since quite a long time. So it's a purely excitatory model, and either if there is no outside stimulus, either the model will be silent in the long run, or we will have persistence of spiking, of spiking activity, which we interpreted as working memory. And we see that on this simulation here, where we see that the system which initially starts here is attracted to some state where there is a sustained spiking activity. So this brings me to the question of long-time behavior, so the long-time behavior of the finite systems and also of the limit systems. This is related to metastability. And so I cite one of the early results by Alini and Guilherme, which you all know maybe. So they showed that isolated systems of spiking neurons, if they are purely excitatory, and that they stop spiking almost surely after a finite time, which means that for the finite system in this submodel, the only invariant measure is the all zero state, which is the silent state, which is of course not what we want. But we can see that as the number of neurons tends to infinity, so as n tends to infinity, this zero state is actually not stable. It becomes unstable, at least for some values of the parameters. And since the finite system also seems to be attracted to some metastable state. So I try to see how much time I have. I have 5 minutes. So actually, we can explain that in the pure Hawkes model, where there is no reset to zero, because in the pure Hawkes model, the limit system, the membrane potential of each neuron is actually described by an ordinary deterministic differential equation. So x of t, which is the deterministic membrane potential, is, so you see the leakage at exponential rate, and we see the influence of the synaptic interactions, W, the synaptic weight, times F of x of s, so the current membrane potential value of each neuron. So if we wonder what are equilibrium states for the potential, and that means also for the intensity of each neuron, we just have to solve a fixed point equation, okay? And it turns out, so if you write this fixed point, I mean, if you trace the graph of f, it depends on the shape of f, but in some cases when it is concave, so this red line here is f, which is renormalized by the potential divided by the leakage rate. No, not the potential, the synaptic rate, sorry. So it's little h, it should be w. Anyhow, we see that in some cases, if initially we kick out of zero sufficiently fast, then we have an attracting second fixed point, which is actually the metastable state. Okay, so this is for the pure hogs. For the Galvez-Löcherbach model, it's not so easy to prove that we have basically the same picture. Well, so we can't directly apply these arguments to the true process with discontinuities due to the reset jumps, but we did it mathematically in a paper together with Pierre Montmarché, who got interested in these kinds of models. And so we were really able to prove that we have metastability in the true GL model where we have reset. And so this means that we can argue that, at least in this model, the system remembers some cognitive tasks, which are the initial inputs during a long time, and the time duration of this remembering of this memory is asymptotically exponentially distributed. And I think there will be a talk by Morgan later today on this metastability, and there have been a lot of NeuroMat young researchers who have been working on that. And Ludmila and Miguel have just submitted something to SPA, which has been accepted for the special issue for Anton. Okay, I skipped this because time is running, but I just wanted to tell you that these models have, well, people got interested in them. And this is a guy from Nice. He did a thesis with Etienne Tenré and Romain Welz. And he was interested in studying the stability of the invariant measures of the mean field limit of the GL model. And actually, it's just to tell you for those who are interested, so that's purely mathematics, but it's possible to understand if an invariant measure of the Nekin-Vlasov equation is stable or not. You know that for ODEs, we just have to take the Jacobian of the drift in the fixed point. And so here's also a derivative that is popping up, but it's more complicated because it's a nonlinear model. But people got interested in it, so there's a lot of research activity that is going on. So for example, right now with Quentin Cormier and Valentin Schmutz, we are working on these kinds of questions for a short-term depression model, which is still in a GL mean field framework. And we are really able to calculate these criteria that assess for the stability and to prove that in some cases we have sustained oscillations. Okay. Sorry, I have to, it's very hot in Paris. So far I was only speaking about the models and that we use the model to understand dynamics. Of course, we can also go in the opposite direction and ask what can we learn about the process from data. You observed that I didn't speak about that. I hope that Guilherme will speak about that. But it is, of course, a very interesting research direction. And I wanted just to show you this slide where I mention some statistical results that have been achieved in this class of models. So we have the estimation of the underlying interaction graph. There is this work by Emilio, Antonio, Giannanapo, and Mauro, who really exploit the fact that we have reset to estimate the interactions. And I guess that Guilherme will speak about his work with Julien. And also right now we finished a revision together with Aline and Kadmo and Dasha, where we estimated the spiking rate of a neuron system in a non-parametric way. Okay, so I have to stop, I think, because in Brazil people are very punctual. So I just wanted to close on a bunch of open research directions. Some of them are already, people started to work on that. So concerning the long-time behavior of the limit system and of the finite one, there are a lot of open questions that remain. They are also related to the question of metastability. Can we achieve that beyond the purely excitatory case? Can we do it in models with several populations or with a spatial structure? Would be nice to have limit models where the mean field assumption is replaced by a sort of local mean field assumption, so convergence to processes on graphs. And for the statistical inference, there's a lot of things still to do. I think that's brand new and a very modern topic. So the main question is, what can we infer about the underlying graph, for example, if we observe just the point process or parts of the point processes which are evolving on it. So I think I have to stop. So what remains after 13 years? So I tried to convince you that we have succeeded to build a rigorous stochastic theory for spiking neuron networks, where we have a precise and mathematically rigorous transition from micro to macro, which allows us in some cases to explain collective behavior. This convergence from micro to macro opens the road to a lot of statistical inference in some cases, and there are a lot of exciting and open questions that are still ahead. And so I thank you for your attention. I'm very sorry that I'm not there. This is a photo of one of the workshops that we had at the IHP trimester, and so I really wanted to thank NeuroMat for these wonderful years, and special thanks to Claudia, Antonio, and Christoph. Thank you.
Okay, thank you very much, Eva, for this nice talk. We have some minutes for one or two questions. I think we have one from Mauro Piccioni here in the... Mauro, maybe you can speak if you want to ask. I don't know, or maybe it's a mistake.
Maybe you can just read it. I
Okay.
think he has. He wanted to congratulate. Thank you, Mauro.
Okay, okay. Thank you very much. There is some questions for Eva. Okay, I have a very, very fast question. Do you think in these next steps, do you think that you can incorporate some community structures and your models of spiking neurons?
You mean that they are arranged in like in stochastic block models?
Maybe, but with time evolution, because some time evolution models with maybe with some behavior depending on a community structure of the neurons.
For sure, you can add this. So evolution of the synaptic weights depending on in which community you are and things like this. Yes, I'm for sure. The question is what is then the analytical tool that we have to study them. So what do we want to prove?
Okay.
Or to describe, but it's for sure that we can arrange these models in well, spatially or community depending, yes.
Okay, thank you. And other questions? Okay, so thank you very much, Eva. Let's thank again, Eva.
Thank you.
Nice talk. Okay, our next speaker is Guilherme Ost from IMPA now, I think, or Researchat.
Almost there. Almost.
Okay. Nowhere. Yes. Yeah.
That's why
it's
not
have
clear.
Affiliation now at this moment. Okay. Yeah. So thank you very much, Guilherme, and he's going to talk about rigorous statistical inference for large but partially observed networks of neurons. Thank you. So maybe if you can speak 35 minutes, and then we have some minutes for questions. Okay. Thank you.
Okay, I will try. Okay. So thank you very much, Florencia, for the introduction. I also, before starting, I'd like to thank Claudia and Antonio Roque for organizing this closing NeuroMat workshop. And as you can guess from my title, I'm trying to summarize or give some information about the results that I have been that I have obtained with collaboration with colleagues in NeuroMat related to the statistical inference of a network of neurons. Okay. So just to be sure that everybody is on the same page, let me try to define or to state the problem at the very high level. So what is this problem of that we are interested in? So we have data which comes from spike trains. So we observe the activity of a certain number of neurons. So in this picture here is 13. And then for each neuron, we observe a sequence of moments at which we have a spike. And here, as you can see, so here's the time on the x-axis. And we basically are considering a discrete time version of the data in which we discretize the time in very small bin sizes. And for each bin, we assign a symbol 1 if we see a spike and a 0 otherwise. So the black squares here represents a presence of a spike, okay? So we are given this data, and what we want to do at the end of the day is to, for each, is to obtain, like, is to come up with a statistical procedure that outputs a graph where the vertices of this graph corresponds to the recorded neurons, and the edges of this graph represent a certain type of interaction between pairs of vertices or neurons. And of course, I mean, sometimes you might not necessarily be interested on this graph itself. You might want to understand just some features of this graph. For example, what is the density of connections that we see, that we imagine that we have in this graph, or perhaps you want to say, among the neurons that you observe, which ones are inhibitory and which ones are excitatory, for example. So this type of questions that we are interested in to understand. Okay. So I hope this is more or less clear, the problem formulation. And then what I want to do next is just to briefly summarize some of the results that we obtained over the years. And then I will try to highlight perhaps the last work that I have done together with other people that I believe that can have something very important for the future. Okay, so what I can say in terms of results. So with respect to the question of trying to recover the graph itself, I guess the first paper that we have was together with Aline, Antonio, and Eva, so in 2019, where basically we consider a very general model description for the spike trains. So that's why I'm calling this parametric. We can discuss this later if you want. And then basically what our results say is that we can, for really estimate the existence or not of an edge correctly, as long as the interactions, so perhaps something that I forgot that's very important, sorry, let me go back here. So of course, I mean, I said that we have a certain number of neurons whose activity was recorded, but one difficulty of this problem is, as is indicated here in the picture, is that there are several other neurons whose activity we don't observe. And of course, this should be taken into account in the analysis, because otherwise this can lead to some spurious interactions, and we need to take this into account in the problem. Okay. So I was saying in this paper from 2019, we are able to correctly estimate the existence or non-existence of interactions as long as the interactions from the unobserved neurons are sufficiently weak. We have a very precise way of saying this. And more importantly, I think one important important issue that we want to understand is the relation between the size of the observed network and the size of the number of time points that we have in our data, which is the relation between these two parameters that allow us to correctly estimate the interactions. And I mean, very informally, I think our results say that as long t is much larger than an exponential, is much larger than exponential of the number of recorded neurons, our method, I mean, is consistently estimate the interactions. So this says that essentially, if time is extremely big, we can really recover the existence or non-existence of the interactions. And if this is not true, and then we don't know how to do it, at least with this very general model. And then to deal with this fact, I tried with Patricia Renaud-Bourret. So she is also a senior as a researcher and NeuroMat member. We try to use some tools, known tools from high-dimensional statistics, which somehow are called these convex regularization methods, to attack this problem of the estimating the graph. And basically here, the idea is that someone can give us a set of functions to approximate the probability of observing a spike for a given neuron I, given the past history. So we are given the set of functions to approximate this transition probability through a linear combinations of these prefixed functions. And then the problem is that which is the best linear combination, in the sense that which is the best linear combination, which is the linear combination which is the closest to this transition probability. And then once you answer this question, you can really relate the problem of finding this best linear combination to the graph, to the estimation of the graph itself. Okay, and then basically our result says that, okay, you might have some dictionaries, some functions that you use, which really gives you the best approximation. So this is sometimes called the oracle, provided that t, so here again, the number of time points has to be much larger than the log of the number of functions that you choose. And in particular, the point here, there is no dependence on the size of the network. So this indicates that in some cases, this method really allow us to consider very large network of neurons, which can be something very interesting in practice. But the point is that this property holds just for, this property doesn't hold in general. And if you want to to consider much more complex dictionaries, you ended up again with a condition of the type t has to be much larger than the exponential of the number of the recorded neurons times a log term, which depends on the size of the number of functions that you use. And again, it seems that you are stuck in the situation where, of course, where you can only consider networks of a very small size. And then, I mean, this really leads us to the question of, can we really escape this curse of dimensionality? Can we do something about this? And to better understand how to deal with this fact, so I decided with my colleagues to analyze much simpler spike train models. And I would say that for this multiple spectrum model, the focus for the time being has not been on estimating the graph of interactions, but rather we have focused on estimating features of this graph. As I said at the beginning, for example, like the density of connections, or if I can discriminate, for example, which neurons are excitatory and which neurons are inhibitory. Okay. And in particular, so in this framework, in this direction, we recently, together with Julien Chevalier and Eva, we published a paper where, for this very simple toy model that I'm going to present in a minute, we are able to estimate the density of connections. And we prove that this can be done, for example, with T is much larger than the square root of N, something which is a much weaker condition than the condition for estimating the graph. And I should mention here that this capital N here corresponds to the number of total neurons in the network, whereas in my previous slide, this little n here corresponds really to the number of recorded neurons. So this means in particular that for the time being, we are forgetting or not considering the fact that we have partial observations. Okay, so this is something that for this model, we are still not there yet. Okay. And what I want to do in the remaining of my talk, so in this essentially 15 or 30 minutes, I want to highlight recent results that I obtained with Julien Chevalier on this problem of discrimination between excitatory and inhibitory neurons. And in particular, I'm going to present this time model that we have been working on. Okay, so that's the plan for the rest of the talk. So what is the model? So the model, for defining the model, first we say, okay, we don't know exactly how the network looks like. So we are going to consider the simplest possible model for describing a network, where the vertices of this network are partitioned in two sets: the sets of excitatory neurons, so this is the P+, and the set of inhibitory neurons, which is this P-. Okay, and this set here is just a notation for the set of the first n integers, which corresponds in my notation to the set of all neurons. Okay, so we have the partition of the vertices of the graph, and then for each pair of neurons, we consider a Bernoulli random variable with parameter p. They are all independent, and if this random variable bij is equal to 1, means that there is an edge, directed edge from neuron j to I. So there is a direction here which is important. And in the model also there is this parameter lambda, which somehow plays the synaptic weight that Eva was mentioning in her talk. But here we assume that is a very homogeneous network. So and we codify all these elements in a graph that I'm denoting here by theta, and the entry ij of this graph is just 1 minus lambda divided by n times the existence of an edge from j to I, if this neuron j is excitatory, whereas if the neuron j is inhibitory, it's essentially the same, except that we put a value minus. Okay, so this is the graph that we consider in our model. And then the second thing in the model is like, conditionally on this graph, we have a dynamics for the spike trains. So here we have xt, here is the configuration of all the spikes at a given time bin. And we assume that conditionally on the graph, we have a Markov model, which is stationary. So this means that to describe the state of the system at time t, we just need to keep track of the information of the previous state. And we assume, moreover, that given the state of the system at time t-1, so the configuration of all the spikes at time t-1, all the coordinates at time t are going to be independent, and which one in the coordinate, the ith coordinate will spike with a probability which is denoted by this pi of theta. So depends on the graph, depends on the neuron, and of course depends on the previous configuration. And we consider a very particular form for this transition, which is, as you can see here in the on the screen. So there is this parameter mu here, which plays the role of the baseline parameter. And then on the other part here, we have two sums. So the first sum here just says that for a neuron I, it looks at its neighbors and make an average of the number of spikes of the neighbors which are excitatory. So this is the first term. And in the second term, we have something which is kind of the opposite in the sense that, so this is again an average if you want, and then we are doing an average effect over the neighbors of I which are inhibitory. And the point here, just to stress that, which is important here to interpret this as inhibition, is that whenever a neuron J which is inhibitory spikes, this value, the value of x j t-1 is 1, so this is 0. So really this really decreases the probability of observing a spike for I in the next time. And just to have just to be sure that we have really a probability distribution, no matter the realization of the graph, no matter the configuration that we observe, the parameters mu and lambda, they are constrained in such a way, but this is just to be sure that we have always a well-defined model, okay? And so for this model, the question that we wanted to understand is, okay, I give you the spike trains of I give you the spike trains of these n neurons, and I really want to know which neurons are excitatory and which neurons are inhibitory for this model. And throughout our analysis, we assume that we don't have any information from the parameter mu, lambda, nor the graph, so these are not observed. And however, we assume that the population of the excitatory neurons is proportional to the number of total neurons in the network. So this n times R plus. Similarly, for the inhibitory neurons, so the size of the inhibitory neurons is n times R minus. And these parameters, they are both positive and sum to 1, but the values of R plus and R minus are not known. Okay, so basically we are not assuming very much on the model parameters. And to solve this problem, we have a very simple solution, which is the following. I try to explain here. So the solution is as follows. So we are given this data. We compute the average of the spikes for all the neurons. So this is representing this n hat. And then we compute an average of how the state of the system at time t is correlated to the state of the system at time t plus 1. Okay, so this is precisely the meaning of this what we call here one-leg empirical convergence matrix. Once you do that, you define a vector that we called here sigma egg, which basically for each coordinate, for each column of this matrix sigma, you sum over all the rows of this matrix, you obtain a number, and so these numbers define this vector sigma egg. Once you do that, you just apply some clustering algorithm. In our results, basically we focused on the case of a k-means clustering algorithm with k equals 2 because we have two communities, so we applied the k-means with k equals 2. And then and then after doing that, the communities, one of the communities we call this P plus, and the other P minus. Okay, and you can really show that for this metric here. So for a given estimated partition, if we define this MR of this estimated partition as just a proportion of misclassification, we can prove that in fact, with high probability, the misclassification is smaller than this quantity here. So this expression, which depends on the size of the network and the number of time points. And the point here of this result is saying that rather than trying to rigorously understand what it says, is that this method is really have the misclassification going to 0 as long as this term here, so this term here, which means that n divided by t essentially has to be very small. Provided this condition that t is much larger than n, we can prove that with high probability, such a simple method works for this model, right? And moreover, we can prove that in fact, this condition here, so this condition here, t has to be much larger than n, is indeed necessary. We cannot avoid this in this type of problem. And when you combine these two results, the conclusion is that essentially our method is the best we can do for this model. Okay. And I mean, I just want to emphasize that in our results, in fact, we need that t has to be larger than n times a log factor of t. But usually people in statistics, they tend to neglect these log terms. And that's why I was saying here that t has to be much larger than n up to log factors. And we can prove that, in fact, this cannot be essentially improved. Okay. And then just a few remarks. I mean, there is another notion that I'm sure that Florencia, for example, knows, that there are, you may ask yourself, you can really not only control the proportion of misclassification, which is already something important in practice, but also to control the probability of recovering exactly the graph. For this same model, for the same model and method, we can prove that if t is much larger than n squared, a modulus some log factors, we can also have exact recovery. And our theory, in fact, I mean, allows many other possible clustering methods, like a hierarchical method, or what we call the mean and threshold. We also have results for a spectral method, which might be useful for other more general models than ours. So that's why we decided also to study spectral methods. Yeah, so that's just remarks that I had in mind. And I don't know if I have how much time I still have.
You have 2 minutes.
2 minutes, yeah. So yeah, so so the point is, okay, so we have this theory that says that if we focus, for example, in the problem of detecting the communities, basically we need that the time, the number of time observation is just larger than the size of the network, not an exponential number in the size of the network. So it's something much weaker, much weaker. And so we have theoretical results, simulation results that I will skip here. And then I just want to emphasize what is the key result behind all this machinery that we developed, which I think at the end of the day help us to understand the problem of estimating the graph itself. Okay. So this is what we call here this, I called here key structure result. And try to explain this shortly, but still precisely. So imagine that I fix the graph. So I fix the graph, and then I have the dynamics of our Markov chain. So what quantity that is behind of all our results is the covariance. It's how the activity of a neuron J at a given time, let's say 0, because the process is stationary, maybe I forgot to mention that, how the activity of a given neuron at time, the neuron J at time 0 is correlated to the activity of a given neuron I at time 1. So this is something that conditionally in a graph, I can compute this thing, but if the graph is random, so this quantity here is going to be random as well, okay? And so I denote here sigma 1 just to is the matrix where I collect all these conditionally covariances. And so this is one hand. On the other hand, we have this matrix A here, where the entry ij is given essentially by the graph. So here I have, if I take a column which is in P plus, the entry ij is just the graph itself divided by n. And if j is inhibitory, I have the graph again itself divided by n with a minus sign. So essentially, in terms of using the language from the community detection, so this A would be the adjacency matrix, essentially. And what we can prove, in fact, is that when this matrix sigma 1 is random because the environment is not fixed. This is something random. And what we can prove is, in fact, that this matrix sigma 1 can be decomposed in a sum of 3 matrices, where the first matrix here is proportional to the adjacency matrix. So the constant C1 and the constant C2 here that you see on the screen, they are explicitly given in terms of the model parameters. So that's not very important, but we have a very precise expression for those constants. So the first term here is proportional to the adjacency matrix. Here we have a bias matrix in the sense that here Jn is just a matrix with all entries equal to 1. So this is something which is a bias term. And then plus an error matrix, which we can prove that uniformly for all the entries, this is smaller than something like a square root of log n divided by n cubed. And this is important because you see in both matrices here, the C1, C2, Jn, they scale as 1 over n. Okay, so this is something also important. So this is scales as 1 over n. This is some feature which is known from the literature of mean field models. And the error here is something which is much smaller than this. Okay, so that's important. This expression here, what is important is that it's much smaller than 1 over n. Okay, and so this is saying that, in fact, this matrix here, this conditionally covariance matrix, is very related to the adjacency matrix, which is related to the graph itself. So this is saying that if we are able, in fact, of getting rid of this bias term, which there are some general, procedures to do that. In fact, just by studying this covariance matrix, we might be able to estimate the whole graph, in fact. And the point is that estimating this covariance matrix is much faster than, you can do this for much smaller sample sizes. And in particular, this would lead to a condition much weaker than t has to be smaller, exponential larger than the size of the network. That's my whole point. And in fact, we are exploring this with several people, in particular with Patricia Renaud-Bourret, and also with another work with Roberto Imbuzeiro from IMPA and Guilherme Reis, which is assistant professor in the Federal University in Niterói. And so this leads us to my last slide, in fact. So for this simple model, we wanted to understand a question which was not directly linked to the graph estimation itself. But then at the end of the day, the tool that we used, in fact, allow us to relate some structural property of the model to the graph, to this graph of interaction. And we are thinking of exploring this new result to improve our previous results. That's the message that I want to say. And there are several possible generalizations for this work. And of course, the model is still very simple, and progressively we want to make the model more complex so that we can go back ideally to a very general model and still be able to estimate the graph with a rather much weaker conditions. So I'm sorry, maybe I passed my time, and I stop here. Thank you very much.
Okay, thank you, Guilherme, for this nice talk. No, I think you begin a little later, so it's okay. Some questions? No? Okay. We have a comment, very nice results from Mauro. So, yeah.
I just want to say something. I apologize, Mauro, for not mentioning your work with Emilio, which is also related to this, and it's within the NeuroMat program. But yeah, I apologize, because this is also something very important for this problem.
Yeah, here.
Hi, Guilherme, very nice talk. Thank you. I have just a question related with if you have any results related with the fraction of inhibitory and excitatory networks. I believe that when this fraction is like 1/2, you need like the most data to have a good estimation. Can you make any comment about that?
Yeah. So in fact, I mean, in the paper, so if you look at the paper, I should say Julien did the simulations. And so again, the model is very simple, and the parameter values were exactly this. So I have P is equal to 0.5. In fact, all the parameters are equal to 0.5 except mu, which is 0.25, just to be sure that mu is and lambda are constrained as they should be. And for this particular choice, I think the network is balanced. So I have 50% of excitatory and 50% of inhibitory. Our method, which would correspond to this. So in this table here, we have different values for N and T. So you can see them here. And what we plot here are the percentages of the mean classification rate. So it means that we simulate several times, 100 times, and for each time we apply our procedure, and then we compute how many misclassified vertices we have. And you see for for those values here, our misclassification rate is around 2%. And in fact, there is another procedure, which we call this threshold procedure, which performs best for these parameter values. And basically, I try to explain here just very shortly. The idea of this mean threshold procedure is like you take this vector gamma hat, compute the mean value, and do your classification with respect to this mean value. All the coordinates which are above this mean, you put as P plus, and all the others you put as P minus. And so since there is this special symmetry in the problem, this very simple, even simpler than K-means algorithm performs better. But then when you change, for example, when you change the proportion of excitatory, for example, if you increase this, as will be more close to the reality, our result, our method works much better, in fact. And of course, I mean, there is something that is very important that I forgot. For the theory, it was very important that the P here, which controls the density of connections of your graph, is kept fixed. And then, of course, one natural question is if you can allow this to change to scale with n to have sparser graphs. And so this is one of the things that we are currently working with Patricia Renaud-Bourret, and we hope to soon have some results about that.
Okay, thank you very much.
Okay, let's thank Guilherme again. Okay, thank you, Guilherme. And now we have a little break for a coffee. And yeah, sorry. Artur, can you put the messages in the, or because I'm not seeing here. No, in the messages here. Let's see. I think was the previous commands or você pode clicar nas mensagens.
Now he added some comments recently. So he said, oh no, it's I don't know.
Yeah, I think it was a kind of question for me.
Yes, yeah.
I said we didn't use the fact that a neuron is either excitatory or inhibitory.
Yeah.
Of course, it
yes.
can. Okay.
Yeah, I try to answer to him, but yes, Mauro, it's just for.
Okay.
Yeah, just yeah.
Not a question, just a comment. Okay.
Yeah, okay.
Thank you. Yeah. Okay, so thank you very much. We will do a little break now, and we return in 15 minutes. Okay, thank you.
Oui. Mais il y a aussi une traîne pour aller.
Non, c'est dommage. Normalement, au Brésil, on n'a pas de train qui fait les connexions entre les États. C'est un peu triste, ça. Tu peux faire un bus, c'est 7 heures normalement, 7 heures de voyage. Donc, il faut faire le balance 7 heures ou 50 minutes. Mais tu peux pas, des fois, tu peux pas.
Mais bien sûr, ça c'est aléatoire.
Ouais, ouais.
Même en Europe, je pense, tu peux.
Okay, let's continue with our session now. Our next speaker is Morgan Andre from IMEUSPI, and he's going to talk about the pathways approach to metastability and its application to GL models. So thank you very much, Morgan.
Bon. Okay, so thank you very much for the invitation for this talk, which is in time because when I was asked to give a talk to kind of summarize one of the line of research of NeuroMat, I was just finishing a paper with Cadmo about metastability in GL models. And so this is what I will be talking about and trying to summarize all the different results we obtained in the different versions of the Researchat model. But so what is metastability in general? So it designates the tendency of a system to dwell for a long time near an apparently stable equilibrium before a rare fluctuation nucleates on a comparatively short time scale a transition toward another equilibrium. So in short, you could say that metastability is something, any system that has a behavior which is kind of between stability and instability. So it's a notion that has a pretty long history, starting mostly in chemistry and physics, and then was observed and studied in many different areas such as economy, electronics, and specifically in neuroscience. It has become an important topic because neuroscientists believe that the brain is metastable for some reason. And well, I do not really have time to enter into the details of why is that, and I will focus more on the mathematical part. But so from the theoretical point of view, like in math and theoretical physics, there were different approaches that have been developed to study metastability and dynamical system and stochastic process and so on. So one of the first one is evolution of ensembles. There is a piecewise approach, a potential theoretic approach, and spectral approach, and many others. And I will focus on the piecewise approach, so there is a kind of a seminal paper. Yeah. Ah, okay. Okay, so sorry for Guillermo, but so shall I stop and wait a bit, or shall I stop and wait a bit? Yeah, so I'm going to focus on the piecewise approach, which basically was invented after the evolution of ensembles. So I will just quickly speak about this first evolution of ensembles approach, which comes from a paper of the 70s by Penrose and Lebowitz.
And basically, the idea is that so you have some evolutions that it can be either a deterministic evolution like a dynamical system with possibly random initial state, or it can be a stochastic process, typically like Markovian interacting particle system. And so let's say you have some. So S here is the blue part is the state, the general state of the process or the dynamical system. In R is some candidate for a metastable region. And in this evolution of ensembles, the way they characterize metastability is suppose you have some probability measure mu invariant for the system, and you take the conditional version of mu on the metastable region R. And then you consider the probability along time, pt, that the system gets out of this region R, right? So you can imagine, for example, if it's a dynamical system, so you choose the initial state with respect to this mu R, and then the system just evolves, and it can, at some time t, it can be either still inside R or outside R. And what you're going to consider is the evolution of this probability distribution over time t. And one of the fundamental property of metastable systems, so it's not the only one, but maybe the most important one in the three characteristic properties that they gave, is that if you would like the probability to become bigger and bigger as you can change some parameter of the model. So typically the number of particles, maybe the temperature and so on. And what they do is that they look at the derivative of this probability of being outside R time t, and you can prove that the maximum value for this is actually at the origin at time 0. And so you look at the derivative at time 0, and the requisite that you want for the system to be metastable is that lambda can be taken. So lambda is this, so the notation that you take for this derivative at 0. It can be taken as small as you want, as you're changing the parameter of interest. So you might think that typically the number of particles, even if it was not the actual parameter that was considered in this original paper, which is a way to capture the fact that the escape from the region R can be very, very long for relevant choice for the parameters. And so then there was another paper in the 80s by Cassandro, Galvez, Olivieri, and Barres called Metastable Behavior of Stochastic Dynamics, a pathwise approach, which was kind of an alternative approach to this evolution of ensemble by Penrose and Leibowitz. And they did this observation that one of the problems that you have with this approach is single trajectories dwell for a long time in the pseudo equilibrium. You have difficulty distinguishing between two different, very different situations. If you're looking only at the probability distribution or the probability of being outside the metastable region at time t, right? So you're just looking at the evolution of a probability measure over time. It's very hard to distinguish between the situation which is actually metastable, where you have single trajectories which dwell for a long time near pseudo equilibrium before making a sharp transition to the true equilibrium, and another situation which is completely unrelated to metastability, and every single trajectory will go outside R, but in a very slow and smooth way, with where we don't have this sharp, pseudo-stationary phase for some time, and then a sharp like tunneling to the outside of the metastable region, which is basically, you can see it that way this picture here. So typically you will look at some energy profile, like your free energy, and the metastable, which is the left one, where so you can imagine that the ball is kind of getting randomly on the left and on the right, and you can see that in the situation on the left, it will stay in this valley on the left for some time, but at some point, because of some random fluctuation, it will eventually get here and then cross the energy hill and go down the actually metastable states. While if you're not looking at every, so it's called pathwise because you're looking at individual trajectories and estimating the probabilities, and if you're not doing that, you could not see the difference between this situation and this situation here, where you basically have just a very, very flat slope, and you can take it as flat as you want if you changing the parameter in some direction, and it will just very slowly go to the equilibrium. But this is not metastable at all, right? You just have one stable equilibrium, and the system just goes there in a straightforward way. So, as a result of these observations, they propose the pathwise approach to metastability, which is so imagine you have a Markovian system of n particles, and you have two fundamental properties for characterize metastable systems, which is first, you look at the extinction time on some macroscopic timescale beta n, and it has to be to converge. So it's always an asymptotic property when n goes to infinity, and you expect if it's metastable, you expect that this extinction time, the time it takes to get out of the metastable region, will be exponentially distributed. And this is because of the memorylessness of exponential distribution, right? And so this kind of already capture a bit of the pathwise perspective, because I mean you can differently from this perspective where you look at the probability distribution over time t. Eating time, you can see it as some kind of functional over trajectories that give you some information, and it captures some of the information on complete trajectories. And the fact that it's memoryless, it means that you cannot. So if you know that the system is alive up to some time t, it gives you no information about what's going to happen in the near future. And then you have the second property, it's called thermalization, which can be expressed in this complicated mathematical way. But basically, it means that you have another kind of smaller mesoscopic time scale, on which, if you look at basically any kind of spatiotemporal statistic on the system over this mesoscopic time scale, you'll see that for big N, it's close to some kind of constant value. And so the system is just wandering you nearby some fixed equilibrium. This is before the escape from the metastability region. So, and what about Galvez-Flechover model? So let me just define in a general way what I mean by Galvez-Flechover model or GL models. So basically, I mean, on the most high-level viewpoint, GL models are interacting point processes. So you can imagine that you have a family of point processes on the timeline, so positive reals, and the point of this point processes are the spikes of the system. And like almost any other point process, I mean, the formal way to define it is that way. So you look at so any small interval, infinitesimal interval, you have one spike at some rate lambda it, where I is for neuron I, and you have two spikes in a very small interval with probability 0, basically, and that's all. And the difference with typical, like a simple Poisson process, this kind of thing, is that we are looking at the conditional probability with respect to the filtration of the system. So basically, this lambda it, the rate of the spiking, is something random that depends on the path of the process, right? it depends in a non-linear way. So you have the membrane potential, and the spiking rates is basically a function of this, typically non-linear function of this membrane potential that I call phi here. And the membrane potential is just a value for any given neuron as a given neuron potential, membrane potential that depends on the filtration of the system. And okay, and so what's really matters is how you define actually this membrane potential, right? How it will integrate the spikes from the previous activity of the system. And so I will define this in the next slide. But a last thing is you have also a synaptic weight, giving you for any two neurons the strength of the connection. It can be either positive or negative, meaning that the connection can be either excitatory or inhibitory. And that's all. And under very weak condition, you can show that the system is well defined. So, but so this membrane potential, how is it defined? So you have different version. So I call it GL model with the S, because actually you can define various different variants of this systems that are more or less equivalent, but use different mathematical tools to model the dynamic of the system. So maybe in particular, one of the differences is how you will model leakage. And so maybe the most straightforward and biologically realistic is continuous leakage, what I call continuous leakage, meaning that so the leakage is just the fact that the moment potential tends to decrease continuously over time, and you will model that just by some function here, G, that will tell you how fast a neuron basically forgets its past. And here you have the spike. So anytime a neuron spike, it transmits some excitation or inhibition towards the other neuron. So a given neuron is integrating the spikes of all the other neurons, so just kind of getting some input, positive or negative input at each spike of the other neuron in the system. And whenever it does, the neuron itself spikes, it will reset itself, right? So it was at some value for the membrane potential, and just get to 0, which is included in the model with this LIT, which is a formal way of representing the variable length memory of the neuron. And one particularly interesting instantiation of this model is when you take GT as an exponential function with some rate alpha, right? It's a negative exponential. Because first of all, it's quite a natural choice from the biological point of view, because this is the same kind of thing that were used in more classical, like Leaf, Lapik model and Hodgkin and so on. But also it makes the system Markovian. Right? So what we have here, when you look at the system of membrane potential, so you have the evolution over time for all the neurons. You have a PDMP, so what is this? Deterministic piecewise deterministic Markov process. Meaning that you have a jump, but in between jumps you have this exponential decay, so which is deterministic, and this is the piecewise deterministic part. And you can write so the dynamic of this whole system in a more compact way using just a classical theory of Markov processes using the infinitesimal generator and so on. How much time do I have? No. 5. Okay, and so another way another way of modeling leakage, which are a bit simpler, mathematically speaking. It's a bit less realistic biologically, but it makes the model more tractable. Is our total leakage and unitary leakage. So total leakage, the idea is that you will just model the leaks as another point process, and at each of these total leaks, the system just abruptly not the system, but the neuron abruptly lose the value of its potential. And unitary leakage is the same kind of thing. We have also the point processes for the leaks, but instead of losing everything, every membrane potential, the whole value of membrane potential at any of these of the atom of this point process, we will just lose a unitary amount of membrane potential. And so these are three versions of the Galvez-Fleischhaber model. So two references for the continuous leakage. So there is many more references actually, but these are maybe the two that are more relevant for the question of metastability. So there is this paper from Aline Duarte and Guillermo Ost, which is not about metastability, but they looked at the extinction time, right, the eating time, and proved that it was almost surely finite under some weak condition, which is necessary to then consider proving metastability. And then metastability was proven in a specific version of this continuous leakage in a paper from Eva Locherbar and Pierre Montmarché in 2022. And this is not working anymore. Total leakage, so there was a few papers that I did during my PhD thesis and then during postdoc period. And where you have, I would just consider a simple version of the system where you have one or kind of binary activation function, just basically a simple interacting particle systems. And there is a paper also from Cadmo, Lysa, in the same kind of setting, meaning total leakage, but with a function that is not binary, but it's an exponential function for the activation function. And then there is unitary leakage that was considered by Antonio Marcos de Nascimento, where it's not a result about metastability, but it's a result about phase transition in the system that is defined on a tree, homogeneous tree. And then a paper by, it's the same paper actually, so this paper here, it did both total leakage and unitary leakage. But, so what we did with Cadmo, writing this review, was trying to summarize all the results, but also to kind of highlight the common structure of the proofs and how you get to show a literally significant result. So for the first property of the memoryless extinction time, basically you want to prove that this goes to 0, right? When n goes to infinity, so you're proving that you're losing memory, the asymptotic eating time is losing memory. And you do that usually by getting some bound on this with two different terms. One on the part of the space which are called Wn, and so the one on the complementary of this set. And this Wn is basically the typical configuration inside the metastable region, and the Wn, the complementary of this is the atypical states that you expect anyway to be unlikely for big N. And so the way you prove that both of these goes to 0 is inside Wn. So the first term, it's always some kind of renovation argument where you use some kind of maximal coupling. So you consider two different systems and define them in a way that they will agree the most possible way. Anyway, you understand, they will be the most, they will agree together as far as possible, let's say. And then you can show, so here you have usually a difference between the extinction time starting from two different places, and you can show by this coupling, usually this maximal coupling is goes to 0. And outside Wn, you use some proxy of the system. So usually you can show that either you take the mean field limit of the system, or you have a modification of the system which has some invariant measure mu, and you use the information that you can get and prove with respect to this proxy and its invariant measures to show that this thing goes to 0. And yeah, how many times do I have? I'm dead already. Okay. So I wanted to speak a bit more closely on one of this this paper from Researchat about the continuous leakage, but I will have then to skip it because it's been too long. Just let me mention that there are also many other works on metastability that were done, but in a context a bit different from the setting that I just presented, either because it's mostly numerical results, either because it's not exactly the GL model in the specific setting that I indicated here, or either because metastability is not really studied in the pathwise sense that I introduced in the beginning of this presentation. But yeah, and yeah, okay. So here's a summary of all these results, and so I wanted to end up talking about some of the questions that are still hanging. And so just very quickly, one of the questions is beyond the mean field or complete setting. So many times what you do is so you have many degrees of freedom in the model, right? It can be the activation functions, the type of leakage, and so on. And one of these degrees of freedom is the topology of the interaction graph, and on almost all the results that were done, you have a mean field complete setting, meaning that all neurons are interacting with the other neurons basically the same way, which greatly simplify the proof, and so we are able actually to do the proof in that kind of setting. But if you go out of this kind of setting, meaning that you have some spatial structures, and the things get messy, and the question is, how can we handle this type of cases? So what about animation? Also, most of the results that were obtained in purely excitatory systems. So the question is, how can we obtain such results with inhibitory neurons? Multi-stability, if you have different metastable phases, and you can just pulling from one metastable phases to the other, like continuously, and yeah, so thermalization. So this is the second part of metastability that I speak about in the beginning, but most of the results just focused on the first part. So this will be nice to have some time to take care of the other part as well. And the last one is one theorem to rule the norm. So in this the slide that I just skipped, because the slide about the result from Le Cherban-Montmarché. So one of the remarkable things that they do is that they prove a general result for obtaining metastability for kind of in a model independent way, like for some kind of general Markov process on some Polish space. And the question is whether or not we could use this kind of general result to generically take care of most of the models without having to do very specific hypothesis on the activation, on the various degree of freedoms that you have for defining the model, right? And that's all.
Very much, Morgan, for the talk. Some questions. Okay, we are running out of time, so maybe if you have comments or questions, we can do it in the lunch time. So now, okay, now it's my turn. I will be brief. I first would like to thank Antonio and Claudia for the organization of this nice workshop. As many of BAFA and others talk, we had many workshops during the project, and this is an activity that has been recurrent in the project, and I think it's very nice. We we had the opportunity to do many friends during these 13 years. So my goal is to talk a little about past and present developments in the statistical analysis of neuronal random networks. The title maybe is too broad, but I will only focus in the works I was involved with many many researchers of the project. So first of all, I would like to dedicate the talk to Antonio and Christophe, that unfortunately are not with us. And of course, Antonio was the person who created all this and made this possible, and enable that we could do and participate in many activities and did many friends during these years. And Christophe also was a person that I didn't have the opportunity to work with him, but was a very important person during all these years of the project. So only to talk a little about the history and my personal history in this project. This began when this is a photo from my defense in 2007 here in this not the same room, because it has been renovated, but it was the previous one. And we had here many friends and people that contributed a lot to the project during the years: Pablo Ferrari, Ricardo Freiman, Nancy Garcia, Roberto Fernandez, and of course Antonio, my supervisor. And so we had a long history working with many people that contributed to this project during all these years. And as I said, we had many workshops and activities during these 13 years of NeuroMat. In particular, I put here the workshops that were related to random graphs and random structures in the brain, and statistical analysis of these structures. And so they were very, very important for the activities of the project, and was something that Antonio did a lot. He was very good organizing activities and putting all people together to work in some problems. And I think this was one of the points that made the NeuroMat project to have such a success that many people mentioned today in the opening. So I only put this. Of course, there are other activities in other lines, but I put this because it's more or less the works I did during this year. And from my perspective, past developments that we did here inside NeuroMat, this was one of the first works we did with Claudia, Daniel, that are here, and Andresa Cerqueira, that now is a professor in the Federal University of São Carlos and was my PhD student, master and PhD student. And at that time, we began to discuss about how to analyze random graph data built from EEG data, in this case from the brain. And this was very nice. We had very nice discussions. Antonio was not an author of this work, but of course he is behind, because he was the person who put us in contact and made it possible. So we discussed how to construct these graphs from the brain and how to analyze them statistically. So this one was the first work we did in 2017. And only to talk a little about it, we had some data that was collected in the laboratory, Claudia's laboratory, with an experiment of people seeing like a movie of some light points of a person walking, and we had two experiments. One was like the point representing a person that was walking, and another that was scrambled points. So the idea was to construct some graphs using this EEG data. Here we have a pipeline how we constructed the graphs. So the data was collected during this experiment. The persons, the individuals were seeing this movie, and we had two phases in the movie. One, the visible phase where the person was walking, and another part where nothing occurs. So the data was the EEG data was collected during all this time, and okay, I had to cut the figure because it was very large. So here we have the EEG signal, and then with this signal we transformed this in a correlation matrix between the signals. So once you transform this signal in a correlated matrix, we can, in the next step, construct a graph of this between the neurons. So here is a map of the EEG, a map of the EEG channels, and here are the edges connecting these pairs of neurons using as a base the correlation matrix. So this was a very simple idea, and it's very used in many experiments, and how to construct the graphs. And the idea was to see if we can distinguish the different experiments and the different phases of the experiment, and the two experiments that we had, that was one was the biological movement and the other was the scrambled movement, seeing the samples of graphs we obtained with this procedure. So in the work I'm not going to talk about the details because we don't have time, but in the work we analyzed the random graphs that we obtained, and we developed a test of hypothesis to distinguish between populations of graphs. So here you have a consensus graph for the biological motion. Here is the scrambled motion, there's two experiments, the visible phase of the experiment and the occlusion phase of the experiment. And we saw differences in these different scenarios. So this was the first work we did, as I said, analyzing graphs for biological data, for brain data. And after that, I began to work with communities in graphs. I have an error in the title, sorry, random graphs. So in the second, I began to work with community models, in particular stochastic block models, that are models, probabilistic models that emulate the communities in the graphs. So it's a generative model that shows structures of communities, and this began to be a thing that was somehow there are some people interested in this type of models in the neuroscience community. For example, this is a figure from this work, weighted stochastic block models of the human connectome across the lifespan. So in this work, the authors show different adjacency metrics and the corresponding block model that shows this structure. So you can have different community structures in your graph, and this translates into a specific block model. So this was a work showing the use of these models for neural network. In my case, I begin to work with statistical properties and probabilistic and statistical properties of this model, and only some commands why the stochastic block model is interesting for neuroscience. Okay, so these I think are commands in this previous paper that I cited. They say that the human brain can be described as a complex network of anatomical connections between distinct areas known as the human connectome. The fundamental characteristics of the connectome's organization can be revealed using the tools of network science and graph theory. And of particular interest is the community structure of the network, where communities are conceptualized as densely interconnected and sparsely interconnected. Okay, it's a maybe densely intraconnected and sparsely interconnected. I think maybe is the correct phrase. Is an error. So that is, the communities are characterized for nodes that are connected with the same inside the same community, and that has not too many connections with the other communities. But as the talk as Guilherme talked today, we can have other structures as the inhibitory neurons and excitatory neurons that also show community structure in the network. So inside this model, we have some mathematical, statistical, and computational challenges that, for example, to mention some of the problems I have addressed in these years. In general, you have this generated model that is the stochastic block model, but you don't observe the communities in your model. You only observe the graph, and when you observe the graph, you cannot see anything. You cannot see the structure because the nodes are totally scrambled, and you cannot detect only seeing the image the community structure. So the problem is not easy, and you can have different problems. For example, one is to estimate the communities. This means to cluster the nodes in the communities. Another problem is estimate the number of communities with some statistical approaches. This is known as model selection. Also, to propose or study efficient algorithms for the community detection and model selection problems, because computationally these are difficult tasks. And also study or propose more complex models related to the stochastic block model. For example, state space models, random dot product models, and so forth. So one example was the model Guilherme presented today. That is a kind of a stochastic block model for a particular model for neurobiological data. So this study of the stochastic block model gives some works in the last years, some works with Andresa about the estimation of the number of communities in this model, or in a related model that is called degree-corrected stochastic block model, and more recently a work showing optimal recovery of the communities with maximum likelihood. Okay, but as we are running out of time, I will not talk specifically of these works. I only give the references, and if someone is interested, we can talk a little more about them. And talking about future developments, so I talk about the past, the more or less the present or recent past and recent development, and now some future development. Now we have this National Institute of Science and Technology in Stochastic Modeling and Complexity that was approved by CNPq in the last year, and the idea was to continue these lines of NeuroMat. Now NeuroMat is coming to the end next month, and we we submitted this project to CNPq to continue the development of statistical probability and computer science developments and applications in neurobiology and health, trying to do a framework to have to enable the lines of the NeuroMat to continue in this project. So this project is coordinated by Luis Renato Fonches here from IME and Nancy Garcia from IMECI, Unicampi. And in particular, one of the activities that we are planning is a workshop in August about mathematics. How can mathematics contribute to artificial intelligence? So maybe this is one of the future developments we want to put energy in the future, in the next years, as a continuation of NeuroMat. What we can do from mathematics to the development of artificial intelligence for neuroscience or health. So this is our contribution to the next years of these lines. So I would like to thank you for the attention, and we now have another online session, so I will finish here. Thank you very much.
Yes, so let's move to the next activity of this morning session, which is a tribute to Christophe Pouzat. Hello, hello. Can you hear me? Guilherme, yes? I can't hear you. Can you hear me, Eva? Oh, we can't hear you. Yes, not yet, but it will come. A gente não escuta eles.
Vocês não, vocês nos
okay.
escutam?
Yes.
Okay.
Now it's fine. Thank you. Thank you very much. So let's start again. So the next activity will be a tribute to Christophe Pouzat. Thank you for your presence, and we are very touched by the willing of our colleagues and people from NeuroMat to this activity here today. So we would start with Christophe's contribution to neuroscience by Alain Marty. Yes.
Do you hear me?
Yes.
Can I show my screen?
You can share your picture, your slides if you want. Yes?
Yes, I'd like to.
Chez moi, c'est le bouton qui est le troisième de gauche. C'est juste à droite de la caméra.
I'm trying. Allow. Can't share your screen. Okay.
Go here, go here. Just wait. Okay, cannot share.
Maybe I should
Go
just
here,
talk.
go back here.
You cannot see my screen, right?
No, we can.
Can you see me?
Yes.
So I'll start. So all of you, or most of you, know the recent kind of graying. Christophe Bouzard. I would like to present the Christophe Bouzard of the end of the 1990s, when he was aged 25 years, something like this. So I met him around that time. He was a brilliant physics student in Paris, and I had my lab also in Paris at the time. And later, he wanted to start a PhD in experimental neuroscience, which is what I did. At the time, my lab had moved to Germany, so he came to Germany, and more or less in 1995, he joined the lab, and he started his PhD thesis with us. So he had a background in physics, but he picked up biology almost immediately, and he started to produce beautiful results, groundbreaking results that ended up in a series of very beautiful papers. I can't go into details because of lack of time, but this was really a remarkable achievement. He studied the elementary signals rising at single synapses in the rat brain, and he in particular followed this as a function of age during early development, which is something that was unknown at the time. And also he discovered a new signal, which was in the presynaptic neuron, but it was a retrograde signal. It was a notoreceptor current, which was totally novel, and which is still intriguing at this time. So all of these achievements are quite remarkable, but also due to his personality, he engaged himself in the group activity. He developed analysis procedures, software that we have still using now. Are you hearing me? No. Nobody's here.
Yes, 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 we hear you.
Okay, because I can't. I have absolutely no feedback. So analysis that we are still using now, and also more surprisingly, perhaps he introduced anatomy procedures that were not used in the group at the time, and that he picked up somehow and introduced for the benefit of the entire group. Also, the most amazing thing at the time for me was that he very rapidly acquired a clear-eyed view of the literature in that field of science. And he pointed out to me cases of over-interpretation of the then prevailing theories about the mode of transmission of synapses, and of possible errors in the publications of prominent laboratories in the field at the time. So from conversations with Christophe at the time, that helped to orient my own research actually up to the present time. And that, of course, you would not expect at all from a beginning graduate student. So when I followed a little bit later the career of Christophe, what was evident was that he was not so interested in promoting his own career, much more interested in improving the quality of the science around him. For instance, he tried very hard to improve the rigor of our approach to statistics of us experimentalists, and that was moderately successful, I should say. On the other end of the spectrum, he also worked a lot, I think, to convince theoreticians to be a little bit less naive about the complexity of biological data. More recently, a few years ago, we organized a course in Colombia, in Cali, Colombia, 2019 course. That was a 2-week course, and Christophe was in charge of informatics. We were in charge of more the experimental part. So quite recently, one of the students of the course told me that she really loved the lectures by Christophe, that previous to that, she thought that informatics was boring, but that Christophe's lecture changed this completely. And she also told me that after the end of the course, so this was COVID years, Christophe continued with webinars, and the students of the course followed these webinars, and they kept active, and they kept in contact with Christophe for many months. And this was very important for them, because remember that this was the time of the pandemics. So I have to stop here, I think. In short, the achievements of Christophe at the time of his thesis work are really remarkable, and they are still influencing our science right now. More importantly, I think what is remarkable is his unique personality, which is made of sheer generosity instead of following the implementation of his career and building a small scientific empire, which he could have done. He was more interested in sharing his knowledge with people surrounding him. So I would like to stop at this stage. Thank you for attention. Do you hear me?
We hear you, but I don't hear the...
Yes, there were some hand claps. Thank you very much.
Okay,
Dr.
that
Alan
doesn't,
Martin,
okay.
for a very nice...
Is there any question,
course.
or maybe we have to wait until the end of the session for questions?
Patricia Renaud-Boré is asking a question, I think.
No, sorry, I was trying to clap, but I messed up with the signs. But thank you so much.
Okay. Patricia, thank you. Any other comment or question? Thank you very much again. So
this
now,
is difficult because Christophe was such a unique character, but I think it will be more apparent from the next interventions as well. Thank you for organizing this.
Thank you, Alan Marty. Thank you very much. Eva, do you want to comment on it? Vera, sorry, Vera raised her hand. Thank you, Vera, for being here with us today.
Thank you so much. Thank you very much, Alain. That was a very touching talk about Christophe. So thank you all. I would like to thank the NeuroMat community to think of Christophe today and to organize this session, which is very moving. I'm with my son, Pascal, and Christophe and I met during his thesis with Alain, and this is full of beautiful memories. Thank you all so much, and it was a pleasure. I had the occasion to be once with Christophe at the NeuroMat in Sao Paulo, and it was a great pleasure for those who remember me to share time with you. Thank you very much.
So much, Vera. Now, Eva Locherbar is going to talk a little bit about Christophe's contributions to neuromathematics, right? Thank you, Eva.
Yeah, I try to share my screen. Just a second. I have to put it full screen now. You all see my slides?
Yes.
Okay, so I start with the photo. Of course, this is a photo that we took when Dasha showed us the forest of Fontainebleau. That was right after the trimester that we organized in Paris 3 years ago, I think, with Antonio, Claudia, Christophe, and me. And you see on the photo, you see Christophe, Aline, Dasha, and myself. So I tried to remember when we started discussing and when I first met Christophe, but actually I don't know, but I can tell you the following. So we have not that many publications together, but they are very important for me. So we wrote one paper together. I will speak about that later. And then most importantly, we wrote this book together with Antonio on probabilistic spiking neural nets. I can hear. Okay, and so I will speak about the book first. So actually, Christophe's contribution to the book was really essential. Antonio and myself, we had some book projects since a long time, but it was only when we started discussing with him that this project started to be alive, and that we slowly understood where we wanted to go and what we wanted to write. And so, for example, he shared his knowledge, which is very deep about point processes and their appearance in theoretical neuroscience with us. He brought to our attention the articles by Willinger. And so I wanted just to advise you to read at least 2 very beautiful chapters of our book, which have been written by Christophe. The first one is, the appendix number B. So the book is written in 2 parts. The first part, which is a general one, and then the second one where we have complementary material. So it is this appendix on the 2 landmark articles, where one of the 2 landmarks is by Willinger. So he discusses this article and he makes the link with the general linearized model. So I just copied here. I can't show anything with my mouse, but one extract of what he was writing. So Christophe is insisting on something which was important for him. So he writes a generic software, which was called GLIM, was already available at that point. So that was in the 80s. And this software was thoroughly tested to fit the GLM model to data. And he discussed, Willinger discussed this software in the paper. So Christophe writes that makes him not only the most important contributor to spike trainer analysis, but also a pioneer of reproducible research. And you know that this was one of the important things in his research interests. Okay, so this was one thing I wanted to point out. So this is in the book, and I also wanted really to invite you, if you have not already done so, to read the chapter 1 that he wrote in the book, a neurophysiology primer for mathematicians. So it's written for half of us here in the audience. He explains everything you should know about neurons, starting from the membrane potential and the action potentials, and not ending with the questions, is there a global reset when there is a spike or not? So do we need to add reset, or can we stick to the classical Hawkes model that we discussed earlier in today's session? Okay, and so in what follows, I just wanted to show a couple of slides because everything, well, almost everything that I know about neurons is Christophe, who explained me with a lot of patience. And in particular, he explained me why we should bother with spike trains, why it is important to have a stochastic element when describing them, and so why stochastic intensity-based models for them are a good modeling choice. So this, I already showed it before. So this is one of the pictures Christophe used to show. After having sorted the spikes of the different neurons, you get the spike trains, so these samples of point processes over time. And why should we study spike trains and not the exact evolution of the membrane potential of a neuron? Because, and this is the answer by Christophe, I completely copied it of his slides. The key working hypothesis in neuroscience is that it is the time when the neurons spike and not the waveform of the spikes, which are the main information carriers between brain regions. And this is the reason why it is a good idea to study spike trains and to develop models who will be able to predict the probability of occurrences of spikes in the future without too much considering the biophysical spike generation mechanisms behind. So we don't use Hodgkin-Huxley models or these things. We really use these Hawkes-type models. And this is, I would say, one of the main axioms that was underlying a lot of NeuroMat work around the GL model. This is another slide by Christophe where he answered to the question why we have to add a strong stochastic element when speaking about spikes of neurons. So for example, we have the stochastic opening and closing of ion channels, which can lead to fluctuating spike trains. And then there are also fluctuations in the synaptic transmission, which are observed in successive responses of the same synapse to the same stimulus, because the number of synaptic vesicles which are released, they vary from one activation to the next. There are states where the ion channels, they can switch from closed to open states, and so on. And so it is clear that we need some stochastic element to model this. This brings me, this is why I was speaking about that. I wanted to rapidly also speak about our GSP paper, which was about short-term plasticity and how synapses work. That was the common work with Antonio, Enrico, and Christophe on a system of interacting neurons with a short-term synaptic facilitation. So maybe I skipped this. So basically here we considered synapses that evolve over time at timescales which are comparable to the spiking activity of the network. And these variations are due to the residual calcium whose concentration is changing over time. And at the point where we wrote the paper, there were a lot of papers in the neuroscience community that had been written about short-term potentiation, but most of them were purely numerical studies. So, for example, there are famous works by Markram, Zodix, Kistler, Van Hem, and Seeholzer. But I think that the work we did with Christophe was, I mean, we proposed a simple model, mathematical model, but we could do precise and rigorous proofs in these models. And in particular, we were able to identify short-term memory with the tendency of the system to keep track of an initial stimulus. And well, that's written here. This is what Antonio used to say about it. These short-time memory, we can interpret that by the capacity of the system to stay in certain regions of the state space which are actually untypical and which we can interpret as a feature of this memory. The technical tool we used is the passage to mean field limit, so to a large population limit together with precise error bounds. And then in the limit we have a two-dimensional dynamical system which we can actually then study. So we did this here. These are simulations by Christoph. So it's two-dimensional because we have the membrane potential and we have also the calcium concentration. And we showed that in the limit ODE, I have to stop also. I'm almost done. So we showed that the limit ODE possesses actually equilibrium points that are not present in the finite system. And of course, that should be related to metastability. This is something he was interested in. And we see this as an indicator of short-term memory. So I wanted just to say this here, the last phrase. So I think this work reflects the way he worked. So we try to capture biological phenomena which are interesting within a simple model by doing still a rigorous mathematical analysis. So yeah, that's all. This is a photo that Vera took of us at some point. So of course, I learned a lot of him. We had thousands of discussions. We organized a trimester together. But above all, he was a good and a very dear friend. So I will stop with this. Thank you. I don't see anything, so.
Very much, Eva. Now I would like to move to Morgan André, who is going to talk about Christoph as a mentor and supervisor. Please. Yes, sure.
Yeah, so I didn't prepare any slide or anything. Well, because I didn't want to share just objective information, you know, in scientific achievement and so on, and the other one did that very well. So I will just tell you three short and highly subjective stories about Christoph and my personal relationship with Christoph. So the first one is Christoph as an advisor. So when I was still a master student in Grenoble, in France, I needed at some point writing a master thesis, right, to complete my degree. And I contacted a professor in Paris, which I knew from my graduation. And this person was not Christoph. It was because I didn't know Christoph at that time, but it was one of its colleagues, Avner Baren. And he agreed to be my advisor. So I went to University Paris Descartes at that time, when the name changed so much during the last years that I don't know how it's called today, but to discuss the subject of my future master thesis. And so I met Christoph at that moment because he was present at this meeting because he was the co-author of the paper which was to serve as a starting point of my master thesis. And so shortly after, I started working on it. And I would frequently go knock on Avner's door to ask questions and try to clarify things and so on. And he was quite busy, and after some time, I think he got a bit annoyed by my insistent questions, and politely asked me to figure it out by myself. So then what I did figure out is that I could maybe knock on Christoph's door, and I quickly realized that he would always welcome my stupid question and take the time to think about it and help me out. And this is basically how Christoph ended up becoming my main advisor. But most importantly, this highlights one of the many qualities of Christoph, which was his natural kindness. And the fact that he would always consider you, regardless of who you were, a distinguished colleague or random master student, or really just any complete stranger. And it struck me retrospectively that if it was not for his kindness, I would maybe not be here talking to you, and I've done something different, maybe. So this was the first one, Christoph, an advisor. So now the second story is about Christoph as a colleague. So as years passed, he went from being my advisor to being basically my colleague, and as such, Christoph was kind of the Rosetta Stone of NeuroMat, right? Because he was a rare combination of substantial biological and physical knowledge, and also a solid mathematical background. And so he was a keystone allowing all the various people of NeuroMat with very different backgrounds to be able to communicate with each other, to understand each other. And he prevented that the most mathematically minded of us drift too far from reality into esoteric abstractions. He was also a very truthful person, and he would always tell his honest opinion in the most straightforward manner. And that I personally liked very much about him, even though I guess it made it seem a bit rude sometimes to some people. And the third story is Christophe as a friend. So I just realized that it's been almost 12 years now that I knew him. And over the years, we've become not only colleagues, but also friends. And in the last few years, it had become kind of a tradition for me to visit him and his family every year in Strasbourg. So I would go there and spend a few weeks in January or February, usually, at the Pouzat family's home, Rue du Canal, to work on whatever we were doing at that time. And so during the week, we would go to the lab at Strasbourg University, and at night, we'll have dinner together with Vera, his younger son Pascal, and sometimes his daughter Sophie. And then have a long discussion on science, cinema, and politics up to sometime late at night. And sometimes it felt like we did not agree on anything, but it never really mattered at all because it was clear that we agreed on all the rest. And the last time I saw him was during my visit in last February. And so given the type of conscience he had, I knew it was possible, if not likely, that this would be the last time I would see him. And being the statistician that he was certainly well aware of the odds. But we just did the usual thing and went to university and pretended that it was just, business as usual. And this may highlight the third quality of Christophe, which is bulletproof calm and modesty. So yeah, that's all. For this reason and many others, I will miss him very much. And yeah, thank you.
Thank you very much, Morgan. Merci beaucoup, Morgan.
Thank you very much, Morgan. He's also thanking. Okay, so now I'll talk a little bit about Christophe Pouzat and NeuroMat. In fact, I made a very short text, and it's called Christophe Pouzat, Antonio Galvez, and NeuroMat. As far as I know, Antonio Galvez and Christophe Pouzat first met in 2013 at the workshop Mathematics and Neuroscience, a Dialogue, held in Utrecht and coordinated by Roberto Fernandes. I clearly remember Galvez claiming that this very shy and brilliant researcher had exactly the profile NeuroMat envisioned, a combination of a mathematician and a neuroscience experimentalist. We later discovered that Christophe had several other unique features that he generously shared with NeuroMat, including rigorous scientific thinking and a strong commitment to open science. In March 2014, Antonio Galvez writes to Christophe, "Dear Christophe, Roberto Fernandes just told me about the excellent presentation of your research in your habilitation thesis. In particular, he mentioned the analogy you drew between a statistical model selection process and the concept of free energy in physics. I reviewed your publications list, and I think Roberto was referring to the statistical methods you developed for sorting action potentials. But before I continue, let me tell you why I'm bringing all this up. I myself have been trying for some time to understand the concept of the quality-price ratio, which has been used in neuroscience, notably by Sporn, as a candidate for the principle of connectome reorganization after a stroke or other type of injury. I'm wondering whether this has anything to do with the principle of free energy minimization. I am trying to place this within a framework of statistical model selection, and I've been asking Roberto for a while how to link the principle of free energy minimization with a model selection principle like the maximum penalized likelihood. It was through this repeated question that he told me about your articles. How do you see the relationship between the principle of free energy minimization and the model selection principle? Best regards, Antonio. P.S. And congratulations on your habilitation to diriger les recherches. I think this email is very typical of a conversation between Antonio trying to convince Christophe to join NeuroMat team at that time. So after this email exchange in early 2014, Antonio and Christophe met again in July that year at a seminar organized in Copenhagen by Susanne Ditlevsen. At this seminar, Antonio invited Christophe to join NeuroMat and visit São Paulo. This first visit took place in September 2014 and marked the beginning of a long series of Christophe's very productive, but sometimes also turbulent voyages to São Paulo, including challenges such as airstrikes and credit card losses, and also a very, very nice visit of Vera and Christophe at some point to São Paulo and to Rio, which was very cheerful for everybody here. Reflecting on this initial visit, João Pechansky recently said, Christophe's visit to Brazil during the early days of CEPI's NeuroMat in 2014 offered one of our first opportunities to adopt a broader approach to scientific dissemination. It was a complicated period. The dissemination coordinator, Professor Hamburger, was absent, and we lacked a strategic vision. Working with Christophe consolidated or even initiated several key actions: film production, Wikipedia editing, uploading to Wikimedia Commons, press outreach on works in development, hybrid events, music production, open science reflection, and organizing scientific conceptualization. With Christophe, we produced NeuroMat's first internal video, which won an award. Christophe embraced all these ideas with enthusiasm, even though they were entirely new to all of us. From 2015 onward, Christophe actively participated in the preparation and curation and served as a conference chair in almost the NeuroMat seminars, international workshops, courses, and several LASCONs. His detailed, beautifully prepared, very cultivated, and clever presentations were a true gift to all who had the chance to watch them. These pearls were often hidden behind his shyness and sometimes excessive scientific rigor. During the COVID-19 pandemic, he attended all the online seminars organized by NeuroMat. He also actively worked on the preparation and production of the Institut Henri Poincaré meeting held in Paris in 2023, as mentioned by Eva. After Antonio Gauss passed away in September 2023, he continued supporting NeuroMat in several ways, together with Eva Loscherbach, by completing their beautiful work, by orienting and exchanging with young researchers, as Morgan told us today, and by supporting our more recent scientific activities. Christophe Pouzat became one of the pillars of the NeuroMat project, for which we are deeply indebted. Today we mourn this incredibly unique person. Thank you very much. So the NeuroMat team prepared some presentation. Yes, the video. This was done by João Pechansky and Thais, with some pictures of the period of Christophe during all these activities, and we just collected them together in a video now. Pedir uma musiquinha. Não?
A big challenge is how we can build models that are intrinsically stochastic and still simple enough so that mathematicians can manipulate them, obtain theorems, and modelers can simulate them efficiently.
Well, thank you all for your presence. The microphone is open for those who want to say some words. Please be free. Dr. Marty? Eva? Somebody in the audience?
I would like to repeat what I think is the defining characteristic of Christophe was his generosity.
Please, Vera, go ahead.
Claudia, can you hear me? Well, thank you so much, Claudia, for setting up this beautiful meeting and for your beautiful memory of Christophe. That was very touching and very nice. I thank you all for this tribute to Christophe, to his work, to his personality, and I very much appreciate all the work and all the pleasure also he has been taking in working with you. It was always a major project for him to go to Brazil and to enjoy the collaborations, and thank you to all of you. Thank you so much.
Thank you very much, Vera. Thank you. So we would like to end the session by thanking everybody for their presence and their words. Thank you.
Okay, thank you very much, Claudia, and all of you for this nice tribute to Christophe. So now is in our program, we have time for lunch, and we return at 2 p.m. Okay, so thank you.
Let me try something else. Can I call you in a moment? I'll call you back.
No problem. Sure.
Okay, let's see. What's going on here? Can you hear me?
Yes.
Can you see anything? No, not yet.
The sound is a little bit low, though.
Yeah, let me first try to see if I can. Share this window.
Great. Now we can see your slides.
Can you see it?
Yes, they are a little bit. Tá pouquinho borrado.
Okay, can you hear me now
perfect.
also?
Good. Ok. Consegue aumentar pouquinho?
Is everything okay, Claudia?
Yes.
Okay. So
the sound is
I'll wait for your command to start.
Oh, okay. Give me just 2 minutes, Leo, please, because we are just adjusting
There's
the
no
sound.
rush. How long should it be?
Can you please keep talking so that we can adjust the
Volume?
Volume,
Oh, yeah,
yes.
sure. Yeah, just how long should the talk be?
Yes, so you have 30 minutes.
Perfect.
Okay?
Yeah.
Perfect. Is the sound okay for you? Yes? Okay, very well. Let's start then, right?
So everybody, can you hear me then? That's good.
Yes. So let's. I'm making a small introduction for you, Leo. So it's a great pleasure to have Professor Leonardo Cohen today with us. Leo Cohen has been a frequent partner and collaborator of the NeuroMat project since the very beginning, and he has been member of the International Advisory Board all this time long. So thank you very much again, Leo, for all your partnership and contributions to the project. Okay, so you can start whenever you want. Thank you.
Thank you very much for everything. Thank you for the input that I got over the years through NeuroMat, and it's been inspiring in a number of ways, these interactions, and part of those are expressed in one of the themes I'm going to be discussing with you. It's been a pleasure also to interact with all of you over the years, and well, I'll tell you a little bit about what we have been working on our end. The general interest in my lab, or one general interest in my lab, has been the study of the neural mechanisms supporting early skill learning or early learning of naturalistic skills, which is something that I have always seen as potentially useful or important in the clinical context, with the goal of allowing patients with brain lesions to relearn skills that have been lost after they are, for example, strokes. So as a background, skill learning involves forming new memories that bind discrete actions, for example, single piano key presses, into complex spatiotemporal sequences, like, for example, a musical refrain or a small song. When we start learning a skill, there are prominent gains that occur very early on that are followed by near plateau performance levels. And then after performance plateaus, there are somewhat smaller additional gains that develop in between practice sessions across periods of rest, a phenomenon that has been labeled as a consolidation or as offline gains. A few years ago, I'm going back actually to 2019, Marlene Bonstrup, who was a fellow in the lab at the time, was interested in trying to understand better how does learning develop across periods of practice and rest. And she asked healthy subjects to practice a key-press piano sequence for 1, 3 to 4 over and over again over alternating periods of practice and rest for about 36 practice trials on day 1, and then people came back on day 2 to retest that skill. What she found at the time is that when people are exposed to this initial practice session, performance expressed here in the form of tapping speed or key presses per second improves very rapidly over the initial practice trials until performance reaches about 95% of maximum, and then somewhat the performance plateaus. And when people come back on day 2 for testing, you can see that there is a small additional jump here. This phenomenon has been termed as overnight consolidation. And at the time, Marlene was very interested in this initial period of very steep learning, which she characterized or defined as early learning, until performance reached this near plateau. What she found at the time, in looking at the performance improvements across periods of practice and rest, was that, and she labeled, or she defined changes in performance during practice as micro-online changes, and those in between practice periods as micro-offline periods. The micro refers to the fact that were periods of practice and rest of only 10 seconds duration. And what she found as a surprising finding at the time was that the total early learning was largely accounted by micro-offline performance improvements that develop across rest intervals rather than practice itself, than during practice itself. This is something that was very surprising for us, at the time, and that was later reproduced in primates and in other human experiments extensively. So in these particular experiments, what happened was that was published last year. It was found in 2 different tasks, motor learning and visuospatial learning, in these monkeys that performance improvements develop predominantly across these rest intervals rather than during practice itself. So the summary of that initial work was that early naturalistic skill learning unveiled, at least for these challenging tasks, unveils predominantly across rest intervals. We found through a number of other experiments that physical and cognitive fatigue during those small periods did not affect these learning dynamics. And we also concluded that micro-offline gains stabilized over time, consistent with a rapid form of consolidation that developed over seconds, really. So these findings, as I mentioned, have been extensively replicated in the literature. So we next looked at the kinematic mechanisms that cause this phenomenon. And this was done by William Kistler, who was a PhD student in a combined PhD program with UCL in London and Sven Bestman. And what we did this experiment in which people learned the task I mentioned, and while their performance was videotaped. And then we used a number of software tools that were just published in Current Biology this year, leading us to be able to characterize the development of combination of digit synergies that allow this learning to occur. So what you are seeing here in the abscissa are the same 36 practice trials when people learn this task I described earlier on. And what you're looking in the y-axis is the percentage use of synergies, including different number of key presses per synergy, from a single digit key press per synergy to much more complex synergies that engage simultaneously 4 or 5 different key presses. And you can see that initially people engage when practicing the task in the first trial predominantly a single key press per synergy, like expressed here in the green colors. To some extent, 2 key presses too. But as training progressed, you can see a progressive reduction in single digits key presses per synergy towards a progressive increase in multi-digit synergies as people get better and better. The next point that was interesting here was that these synergy changes develop predominantly across rest intervals, that is micro offline as shown here, rather than micro online. And importantly, the magnitude or the magnitude of change in these synergies from single digits to multi-digit synergy predicted the magnitude of learning during rest, but not during practice. So what this meant was that high-order multi-digit synergies emerge across rest periods of early learning. They consisted of small, rapid, and overlapping digit movements that predicted rapid consolidation, and raised the clinical question of to which extent or if if we understand which are the synergies that best allow performance of the skill or best allow expert skill, if it is possible both in the context of the clinic as well as in education to train synergies in addition to tasks, as if in, for example, closed loop neurofeedback protocols. Imagine a piano player who is trained on a particular effective synergy rather than generally on a task, or a music student. So this is an interesting hypothesis that we bring up in this paper this year. We then moved on to, or actually we did this before, but for the purpose of this story, we then looked at the possible CNS mechanisms that could support this form of learning. In other words, how can individual key press action representations bind into a consolidated sequential skill across these rest intervals during which performance improves? And we posed at the time that neural replay could be one factor. Neural replay is the compressed reactivation of neural activity representing sequential motor behavior during rest. We know in rodents that reactivation during non-REM sleep is linked to skill consolidation. We also know in humans that fMRI activity in the hippocampus during these rest periods predict micro-offline gains. So we thought at the time that it is conceivable that wakeful neural replay during these rest intervals can contribute to rapid consolidation of skill. In this work done by Ethan Bush and Leo Claudino, who's originally actually from Brazil, we look at MEG activity while subjects were learning this task. So MEG was acquired over 272 channels, source localized and parcellated. We then trained decoders on the practice data. First single subject individual SVM decoders, and then performance was cross-validated in a different data sets in the form of a confusion matrix. We then look with these decoders trained on the practice data at the probability of single key press reactivations during rest data. Then the probability of sequence replay detection, and then the data was significance tested. So following this pipeline, we look at the MEG activity when subjects were learning this task. And this is what we found. Here in the x-axis, you are looking at different possible replay durations based on animal literature that characterize different durations of replay events. In the y-axis, you are looking at the number of replays per second occurring during those rest intervals. And you are looking at analysis of three different periods. Pre-training rest, before people even practice the task. Post-training rest, after practice completely finished. And then at rest intervals, alternating with the practice periods. And what we found here was first that the replay rates triple during training rest intervals relative to pre and post-training rests. That the optimal replay duration was about 50 milliseconds, when the actual behavior, which is the time required to complete the key press sequence that was being taught, was about 1 second. We also found that looking at the overall replaying count, overall subjects and trials, and the inter-replay intervals, that replays did not occur one at a time, separated by regular periods of without replay, but rather they occur very close to each other at very short inter-replay intervals. That is, they occurred in bursts. So we concluded that the train skill, which is the key press sequence, was compressed about 20 times because the optimal replay duration was 50 milliseconds, which is 1/20 of the 1 second duration of the actual behavior. So the train skill was compressed by 20 times and replayed largely in bursts of about 25 replay events for each 10-second rest interval. We then found that approximately 70% of the total variance was in a principal component analysis, was explained by a PC1 component that included the sensorimotor cortex, entorhinal cortex, hippocampus, and precuneus. We also found that the difference in replay events per second, or the increase in replay events per second, was specific for the trained sequence, but not for untrained sequences. And importantly, that the replay rates correlated with rapid consolidation for the trained sequence, but not for the control. Importantly, these results were replicated in invasive studies in humans at least twice last year. And also importantly, in a recent experiment in primates, it was found that the activity during these rest intervals was very important for these jumps in performance. So the black lines are showing the jumps in performance across the yellow periods, which are the rest intervals. The yellow periods are the rest intervals. But if you apply a form of interfering brain stimulation, in this case it was beta, alternating current stimulation between others, during rest, it blocked learning, as you can see here. So in other words, there is a causal link between this rest activity, replay activity during rest, and the behavioral offline gains. So in summary from that work, motor practice elicits wakeful, compressed neural replay. It's predominantly represented in sensorimotor mediotemporal memory regions. It predicts rapid consolidation of skill. So this mechanistic work, then we were interested in trying to find out how does this apply perhaps in clinical settings. And we haven't done much, we have not done too much on this front, but we try to evaluate this in patients with long COVID in a clinical study. William Hayward did this a couple of years ago. And he was able to show that patients with long COVID in this blue analysis, in this blue group, were showed reduced overnight consolidation relative to age-matched controls. So from that work, we are now studying patients with memory disorders, between other things, and starting to look into stroke patients as well, trying to look at the sources, the basis of these perhaps anomalous neural replay in situations of different pathologies. So with this, I would like to thank and to acknowledge a number of collaborators and the institutions that funded this work in our environment, and thank you as well. And I wanted to leave perhaps a little bit of a couple of minutes for questions that could come up. Thank you very much.
Thank you very much, Leo, for this beautiful presentation. So, questions?
Thank you, Cohen, and I'm here. I'm here.
Oh, you're out of the camera, but that's all right.
I need you to stage your peers.
I can hear you.
Okay.
Now I see you.
Okay. My question is about, did you think if we work with a condition with a mental simulation, not with the actual realization of the motor movements, that could be interesting to understand how we can think about the way that we make the junctions of each one of the event and the expectation about that?
It's a very interesting question. It's a very smart question, and it's definitely something that has been in the in my mind, but it has not been done. And to tell you the truth, I'm not planning to do it. I think I'm waiting to some extent for some pipeline to characterize neural replay events from EEG, because that will make life much easier for everybody and will allow a much more extensive investigation than what we were able to do in this case with MEG. But conceptually, it's a fundamental question that needs to be addressed. I completely agree.
Yeah, my other question is about the EEG, but you said before. Thank you.
Yes. I can tell you one more piece of information. I know of somebody in Japan who's been developing, or who has been able to characterize replay on EEG. He recently shared with us because we asked the methods of the non-yet paper, of the non-existent paper, and we are going to be looking at it. But I'm trying to encourage him to publish a technical contribution to address it, because it will allow a much more widespread investigation of this phenomenon than with MEG.
Okay, and I said because we exactly have this data, the data.
Absolutely, I'm sure. That's why I wanted to bring this up to NeuroMat, because that data is probably available in many people's labs without knowing how to analyze it, and this would be very, very important.
Thank you.
Thank you.
Any other question or comments? Okay, so let's thank very much Leo for his beautiful talk, and let's keep in touch. And
thank you, Claudia. Great seeing you.
Thank you very much. See you. Bye-bye.
Ciao.
Our next speaker in the statistician brain session is Aline Duarte. Duarte from Universidade de São Paulo, professor at USP. Thank you, Aline, for giving this talk today.
So I would like to start. Thank you, Claudia and Hockey, for the organization of the workshop and our final event. And Claudia and Hockey invited me to speak about context-free models and how we use them in NeuroMat in this last 13 years. So I will give you an introduction, a more or less mathematical introduction about context-free models and how we use them to do some experimental protocols. And then the results I will leave to Claudia, and maybe Marcela will also speak a little bit about this kind of data, okay? So we are interested in, well, let's just before, well, we all believe that actually brain is able to identify some patterns. Like if I give you a pattern 1, 2, 3, 1, 2, 3, 1, 2, 3 very quickly, you realize that this is a pattern. This is not a doubt. We all believe that this is true, and this is really accepted in the neuroscience, and even for people which are not from neuroscience, right? But what we would like to answer, and I think Antonio was very positive about, is the brain is able to figure it out, or at least understand, or at some point, or at some way, find that actually we can realize even more complex kind of patterns. What I mean by more complex patterns, this is why I will try to formalize for you today. So what is complex pattern? For us, in NeuroMat at least, we believe that a complex pattern is something which is not deterministic. It's a probabilistic sequence, and a very specific kind of a complex pattern or probabilistic sequence, which are the ones coming from context-free model. And when I say it's very specific, it's not very fair, actually, because almost any kind of stochastic sequence we can describe with a context-free model. This is why I will try to convince you today. Okay, so what we want to do is, okay, we know that brain is able to realize deterministic patterns, and I will try to convince you at least that we can do this even for complex patterns, okay? And the first things that I have to define to you is how we will characterize this kind of complex pattern. So for me, in this talk, a complex pattern would be characterized by a stochastic stimuli, or a stochastic stimuli. So I have x1, x2, xn is a stochastic stimuli. If you don't know what is a stochastic stimuli, is for you could be a probabilistic sequence. So I have a sequence, and I don't know exactly what the next step is gonna be, but I have a probability that something is happening at each time. Okay. And for each stochastic stimuli, I will record some kind of data. So could be a physiological data or a behavior answer. Physiological for us would be, for instance, electroencephalographic data or any kind of physiological data you can imagine, or behavior answer, like if the person is in some sense realizing about the complex or not. Okay, so you depend, for the second one, you depend on an answer, a directly or an active answer of the volunteer. So in case of, for me, in this talk, I will keep two different kind of experiments. The first one is when my stochastic stimuli is given by some sounds. So I have here some bits, x1, x2, xn are different kind of bits. So this is, in some sense, is a kind of rhythm. And then I'm recording here some functional data, which is actually electroencephalographic data, okay? And the second type of experiment that I can have is when we have, for instance, a game. So here, my stimuli are the kicker. So the kicker will choose, for instance, left, center, and right, and following some stochastic sequence or some probabilistic sequence. And the volunteer is the goalkeeper. So you have to guess where the kicker is kicking. And then you will choose center, right, and left, depending on what you are guessing. Okay, so your answer here, the performance, is also left, center, and right. Okay, so this could be 1 zeros and 2, 0 1 2, 0 1 2, for instance. We don't need some function here. So I have two different kind of data and two different kind of answers. And what I will try to do today is defining this properly, how we define this stochastic sequence, and how this answer here relates with this, how this y1, yn relates with x1, xn, okay? And then Claudia will speak a little bit more about the results. So for me, I have two kind of stimuli. This 210, 210 could be strong bits, weak bits, and silent units, or right, center, and left. So this is for the rhythm experiment, and this is for the goalkeeper experiment. So for instance, if I start with a deterministic sequence given by 2 1 1, 2 1 1, 2 1 1, this is the kind of pattern that we are not, we don't have any kind of doubt that brain is able to realize, right? But let's suppose that I take this sequence, and then for each one, for each symbol 1, I will decide if I keep 1 with probability 1 minus epsilon, or if I will exchange this 1 by a 0 with probability epsilon. In some sense, for each one here, each symbol 1 here, I'm flipping a coin. And if this coin is a tail, I will keep 1. Otherwise, I will replace 1 for 0. Okay? Then this, we know that the brain is able to realize what is happening. But for this one, which is probabilistic and stochastic, this is what we want to answer. Is the brain able to characterize, in some sense, this sequence? This is what I'm calling complex pattern here, okay? And when I say, is the brain able to characterize, the first things we have to realize is how we characterize that in order to look at for characteristics, right? So how I can characterize this sequence, this is stochastic sequence. And the way we do it is usually, at least with, one way of doing is through context trees. And how we do that? So let's suppose that this root here is the present, which I'm calling xn. And for this line here, I will put all possible events that can happen at time n minus 1. So the step before the present could be a 2, could be a 1, and could be a 0. Okay? If the step just before was a 2, what would happen? Well, after a 2, we know that the way that we construct the sequence, we know that after a 2, I can have a 1 with probability 1 minus epsilon, or I can have a 0 with probability epsilon. This is the only two things that can happen, and I will never have a 2 followed by another 2, okay? So I can summarize that in this line. So each time I have a 2 as the previous step, the next step will be a 0 with probability epsilon, and a 1 minus 1 with probability 1 minus epsilon with probability 1. It will be a 1 with probability 1 minus epsilon. Okay? Okay, so for 2, it's easy, but let's suppose that the step just before was a 1. And then I have more or less a problem, because I have two different types of 1s. For instance, I have the red ones. For a red one, I have two different events that can happen before. I can have, after this one, another one, and after this kind of one, I could have a 0, right? So I'm taking the ones which are coming after a 2, and there is these two possibilities. And I have other kinds of ones, the blue ones. For this kind of one, I will always have a 2 with probability 1. So basically, I have two different cases. I have ones, which can be followed by 1 or 0 with the coin that I'm erasing 1 with probability epsilon, 1 minus epsilon. Or I'm in the case where I don't have choice. I will go to a strong bit just after. This is because we construct the structure like that. So in the end, what I'm saying is actually looking at the single symbol 1, it's not enough. So what I'm saying is type 1 and type 2 of ones, or red or blue ones, actually is the same that saying that I have to look at 2 steps in the past. So if I have a 2-1, I know that I can have a 0 with probability epsilon and a 1 with probability 1 minus epsilon. If the last 2 steps was 1, 1, then I don't have a choice. I have to go to the symbol 2 with probability 1, and so on. Okay, is it clear up to here? And for the zeros, I have also the same kind of problems. I will have red zeros and blue zeros. For blue zeros, I could have a 1 or a 0 with probability 1 minus epsilon. And for the type red 0, I will always have a 2 with probability 1. Okay, so this is the same as saying that actually 0 by itself is not enough to predict what is going on in step n. So I have to look at 2 steps on the past. And then I will look at 0, 0, 1, 0, 0, 2, and so on, in order to predict what is happening in the present. Okay? So, what I'm saying here actually is basically what I just did here was characterize our stochastic sequence through 2 different things. One thing is this SAT, which is basically telling me how I can split all the possible paths in order to have all the options that I need. And for each one of these possible paths, I'm associating a transition probability. So in the end, this SAT and this family of transitions probability are characterizing completely my stochastic sequence. Okay? And we call this the elements of this SAT context, or basically I'm calling context all the leaves of this tree. Okay? So I will just skip the formal definition because I will not have time. Just a small comment, this kind of model was introduced by Reasoning as a universal system of data compression, and in the literature you can find also with the name of stochastic chain with memory of variable length and variable length Markov chains. Okay, so if you remember the first picture that I present you, you have the volunteer and then you give him some stimuli, which I just characterized here as a context-free model, and then the picture leaves some data, right? Something that we are recording. I just explained to you, defined what is the first part. Now I will try to define how we associate the second part, the IN and the XN. So how we define this dependence? Suppose that we are recording our experiments, or the brain is recording the stimuli, and you have seen the stimuli up to time xk. How do we define the dependence of yk given this? Okay, and what we believe in the way that we define it in NeuroMat is actually we believe that this yk will depend on the context associated to this path. So what this means, I'm sorry for the very non-professional picture, okay? Each time I present that, I'm sorry about it, and I promise that it will be better in the next one, but I'm still waiting for the next one. So let's suppose that up to time n minus 1, we have this kind of path. So it doesn't matter what happens here, just matter that we saw 0, 2, and 1, okay? So we know from our tree that actually in our example, 2, 1 is a context. This is the important past, the important piece of the past. We know, for instance, that this part, this 2, 1, will generate xn, for instance, right? And what I'm defining now is actually, we believe that this is responsible also for generating yn minus 1. So this is how we are associating the answer, like the sequence of what you are recording in your data, and the sequence of stimuli, okay? So this means that actually this red one will generate xn, for instance, 0. So now I have a new kind of past. In our example, the past is 1, 0, and this 1, 0 will generate the yn, and the next one, which is xn plus 1, and so on. So for instance, here, xn plus 1 is 2, so this by itself is the whole piece of the past that I need, and I will generate this piece of EEG only looking at this context. So this is the way that we are defining the dependence between what we are recording in the data and the stimuli that we are giving for the volunteer. And in the two examples that I gave to you, this X sequence could be Y sequence could be EEGs, or even the answer of the goalkeeper, the play that the volunteer are doing. Okay, the choice of the volunteer. Okay, I have 5 minutes. What? Okay. This is just the mathematical way of writing that. It's basically saying that giving the sequence of stimuli, I will choose independently how the answer will happen. And how this will be chosen is following, this is a function that actually chooses the context based on the past. So if I look at the past from 1 up to k, this will look at the important parts of the past, and using that, we generate our answer, okay? And we do that independently for each one of these steps. So, just very quickly, okay, I know what is the thing that we are giving to the volunteer, what is my stimuli sequence, what is the answer, and how the answer and the stimuli are related. Now I will be very quickly give you an idea how to estimate things from this part, from the part that you are recording, okay? And how we recover some characteristic, and when I say some characteristic of the stimuli is actually a context tree, okay? So what we have up to here from how to estimate trees from data. For functional data like EEGs, we just have algorithm context and projective method, and this is in red, not because it's more important, but actually is this was our NeuroMat contribution for this kind of model selection procedures, okay? And then for categorical data, which are numbers, okay? When you have numbers, what we have is, for instance, algorithm context and conditional likelihoods, algorithm context plus some statistics of the offsprings. We have BAC, we have should be here also some Bayesian inference, blah, 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 okay? So for categorical, we have some tools already, and what NeuroMat have been doing in the last years is actually using algorithm context in projective method to try to estimate trees from functional data, okay? And this is one of the main contributions of the project. All these methods here are parametric models. If you want to optimize your parameter, you could also use SMC, which is also one of the main publications of Antonio, okay? Okay, just to give a very, very general idea how all these procedures work. So we have here 4 procedures. 3 of them use algorithm context, and this is what I'll try to give you a very naive idea of how it works. And we have also BAC, which is not very similar, which is not the same of algorithm context, but yet use very close ideas of this biggest tree and cutting pruning procedures, okay? So algorithm context in general do the following. Let's suppose that we have a big tree. Doesn't matter how you construct this tree. Let's suppose that I give you to you and you have a very big tree, okay? Which are more or less describing your experiment. What we do is, for each one of these final branches, we will test this statistically. If this branch is statistically significant, we will keep it. And if we realize that actually is a statistic not significant, we will prune. I will not tell you what I mean by statistic significant or not. This will depend on the statistics you are using, okay? I'm just speaking about the algorithm context. And we do that for all possible branches. So I will do that for this and decided, and then I do for the next one independently, and then I decided, and so on. Okay? So in the end, we have something more or less like that. We have a big tree, for instance, here just with 1 and zeros, and then I will test this branch, and I cut it, and then I test one, and then I test the next one, and I cut it, and I prune, blah, blah, blah. And in the end, I have, for instance, this tree. This tree means what? For instance, it means that actually I tested this branch here, and statistically he's significant. This is why I keep it. And then I test this one, and he's also significant. This is why I keep it in my tree, and so on. And for each one of the branches that was tested here, which are not here anymore, for all of them I tested, and for my statistics was not significant enough. Okay, I'm not saying what is statistically important or not, just speaking about the algorithm context. And then this is the first part of the red line that I wrote before in red, right? So I just explained to you what is the algorithm context, and I'm just and now I will define to you what is statistically significant for us. And in order to decide that a branch is statistically significant or not, we use the projective method. And very quickly, what means being statistically significant when you have a branch? And I tried and I used the blackboard, but I always fail, so I will do it again. So what I have here is one branch. I'm not sure that it's good to see it. Let's suppose that I have here 3, doesn't matter. Let's suppose that I have, thank you, I want to test this branch, okay? This is the one which I'm testing, that I have to decide if I want to prune or keep it. So actually what I will do it, I should put it in different colors, like that. This is the branch. For each leaf, we know that we have some sequence associated, so W and V, for instance, okay? So we know that for each leaf, we have some sequence associated. And what the projective method does is, okay, let's suppose that I can take on my data, and I will not enter in details how, but I will take on my data pieces of EEG which are associated with this V sequence, the pink one. And then I do the same for the yellow one, which is W. So I have a set of EEGs associated to V, a set of EEGs associated to W, and I want to test if these two sets has the same law or not, okay? If they are generated by the same distribution or not. And in order to do that, what we do is we take some Gaussian direction, and here we are using Brownian bridges. And we take each one of these functions, we will project in the Brownian bridge, and for each one of this purple function, we will have some point. When we project two different functions, in the end, what we have is just one real number. So for each function here, we will have one point here associated, which is the projection in the Brownian bridge, and I do the same for the green ones. So in the end, I started with two sets of purples and green functions. And after projecting in some Gaussian direction, what I have is some purple real numbers and some green real numbers. So instead of testing different sets of functions, I will test different sets of real numbers. For real numbers, this is not a very difficult statistical question. People do this all the time. We could perform, for instance, here, Kolmogorov-Smirnov test for real numbers, and this will be a test to say that if this is has different distribution or not. So what we will do in order to say that is different or not, is statistically significant or not, is if the projection has different law, so it means that the branch is important. If the projected data has the same law, actually the branch doesn't matter. This is what we are using as statistically significant, okay? So just to be sure, if this is the same law, we prune. So this doesn't matter. Doesn't matter if it's W or V, which is happening. The law is the same. This is the final. This is the final summarizing, let's say. And if this is different, we keep it. Okay. Then I have the results that I will not speak because Claudia is going to speak very quickly. Just to give you some spoiler. Green is good. Purple is like pink is bad, and we have a lot of greens. Okay. And not working. And this is very nice because I think is important, like for a statistical point of view, is the things that we are finding is not by luck. I mean, if you simulate the distribution of the trees, the chance that you got the good tree, which is this one, is very, very small. Okay, and yet we gathered a lot of these trees. Okay, just to make some statistical remark that I'm not sure that maybe Claudia will not, because for me it's important, and maybe for the neurobiologist not that much. And just to finish, now I have a PhD student that we are looking at for other statistics like functional ANOVA and something like that. To change the statistical significant approach to other kind of statistics. And this is just the main references, and thank you. Thank you very much, Aline, for the excellent explanation. Do you have questions?
Any question? No? She has one.
Thank you, Aline. I was wondering, in your projective method with the Brownian bridge, if you have the same EEG segment but only scaled differently, how does this affect your number on your projected method? Because yes, the amplitude is important, but maybe you have, I don't know, an impedance problem, and this will be accounted as different in your method, and maybe it's not like a morphology difference between.
I never tested, but my intuition is it depends. When you say about the amplitude, if you do that with the whole set, because for this pink one we have a set. And for the yellow one, we also have a set. So if I do something with this, the whole set for each one of this function, for instance, if you, I don't know, if you multiply by 3, that you increase the amplitude, for instance, or doesn't matter what we do, if you do for all functions in your set, this would not be a problem. The problem is if you do with a couple of them, or if you see what I mean? But if you transform the function, this would not be a problem in sense of the distribution. You see? I have the feeling that this would, if you do it with the two sets, they will probably not able to, in some sense, give you some problem in the distribution. Because in distribution, this would be the same yet.
They will keep
yes.
the relative differences between
yes,
them.
Exactly.
Okay, thank you.
I don't know, was that your question?
Yeah.
Oh, okay.
I have others, but I'll wait later. Is there any other question? I have a question that you showed the simulation tree, that the slide that you mentioned that is not by chance. Yes, that you require. It was a little bit fast to me, sorry, so I don't know if I got everything. But did you simulate the data and then tested the hypothesis?
Actually, I skipped a little bit, plenty of steps. So, for instance, here is not only a single tree, is actually what we call it a mode tree. For each one of these electrodes, we have 18 volunteers, so we have 18 different trees. And then for these 18 different trees, we get this one, which is a mode, okay? Okay, then what we do here is basically simulate the distribution of the mode. What does this mean? suppose that this is, I think, for the example that I gave today, this is a tree. No, this is the biggest tree, okay? What we do is, from this biggest tree, we cut and we consider all the possible context tree coming from here, okay? We have to satisfy some properties of context trees, but from here we have, I don't know, I don't remember anymore, but we have all these possible trees, okay? And then what we do is we choose uniformly, we just choose randomly 18 trees and generate a mode. And then we do this again, 18 trees and generate a mode. And this, we do this a plenty of times. And this will give you an intuition about the mode distribution of the possible trees, okay? So if you do that, the tree that actually is the true one, which is this one here, has this second red chance of being chosen by luck. This is what we're trying to show here. Is it clear?
Yeah, so it's more about the mode tree.
Yes,
Yes.
yes.
In your miscellaneous.
You could do that for only one tree if you want. You could just without the mode. You take these and then you choose all the possible ones and choose uniformly, but would be uniform distribution.
Because I think about that a lot, taking into consideration that neurophysiological data will have like variability, and maybe you are recovering a tree that it's more about your data variability than
Just by luck, basically. Yes.
Yeah, so you can do this method with one person, for one person, taking into account, do you believe that this will be possible, taking into account your data variability?
Yes, but there is no what you have to, because I don't remember how many trees we have. Let's suppose that we have 20 trees. When you have only one, saying that you can choose uniformly is 1/2, 1/20. You don't have to simulate. You see what I mean? We have to simulate because we have this mode tree.
Okay.
But in our sense, we know how is the chance of taking one tree by luck. It's 1/20.
Okay.
Which is the same for all.
For everyone.
You see what I mean?
Mm-hmm. And if I have time for okay, if you can comment on how deep, more like open question, how deep do you think that this encoding is in the brain? Like it's for like
I think
cognitive circuits.
This is a question for the wrong person. Maybe you should make the same question for Claudia.
Yes, but
in the next seminar. I'm sorry, I have an idea.
Okay,
but as a mathematician, I not risk answer the question.
So we now have a 10 minutes break, and we come back in 10 minutes to the next presentation. Thank you.
Achei que saía.
We start again our statistician brain session. Tá tudo certinho. Um passador. Não, tá tudo certinho. Tá ótimo. Obrigada. Estou esperando aqui as pessoas. Falar mais alto? Ah? Aumentar o volume do microfone. Tá baixinho aí atrás? É? Agora tá melhor. Tem que respirar. Vamos lá? Aline, quer? É.
Claudia, sufficient. So, for our next speaker, we have Claudia Vargas from Federal University of Rio de Janeiro. And, well, let's see.
Thank you, Aline. So, thank you all for your presence here today. As you know, NeuroMat had two main research lines: stochastic modeling of nets of spiking neurons, the session that we had in the morning, and in the afternoon we are speaking about the statistician brain, and I'd like to make it as a tribute to our former coordinator, Antonio Galvez, but also a special thank to all the collaborators to the Statistician Brain Project. So it has been a great pleasure to work with you all these years, and really I'm amazed on how much we gain, we learn, we fight, and we did so many interesting things together, right? So as Aline said just before me, thank you, Aline, your talk was wonderful. I put some more pictures, as you know. The statistician brain conjecture states that the brain assigns probabilistic models to sequences of stimuli as it learns to interact in the world. So what would be these sequences? Some examples here: musical sequences, language, spoken and written language, and also, of course, sequences of sensory motor events. Here we have the great football player Marta doing her a football game, and as Aline said, we are pretty much interested on this topic, and especially today, right, Roque? We hope that Brazil is going to do something good for us. But the question is, can we transform these symbolic sequences into a mathematically treatable object? So this has been the core of the Statistician Brain Project. And in the beginning of the NeuroMat project, we had some open questions. How to extract from brain signals the very structure of a sequence of symbols, and how to establish a formal relationship between this sequence of symbols and the recorded signal. So as Aline beautifully showed 10 minutes ago, the idea here is to have to propose an experimental model and to retrieve from the electrophysiological signals or the behavioral signals a signature of this sequence of events, which will be the model, the mathematical model. The chosen mathematical model was a context-free model. As you well known, Galvez was very fond of the context-free models, which are a class of stochastic models capable of compressing any sequence of symbols generated by a source. So this was proposed by Rissanen in 1983 as an universal compression system. When we started the NeuroMat project, Antonio Galvez, Charlotte Galvez, Jesus Garcia, Nancy Garcia, and Florencia Leonardi were just putting out this very interesting paper on context-free selection and linguistic retrieval from written text. So they were already using these context-free models to extract information from linguistic texts. And we started thinking on a new experimental protocol together with Aline, Guilherme, and then Noslin, Ricardo Freiman, where we had the sequences of auditory stimuli, hand claps. As Aline told you, we had strong beats, symbol 2, weak beats, symbol 1, missing unit, symbol 0. And what we did was to replace the symbol 1 by a symbol 0 with the probability epsilon. And the participant, can you recognize yourself here, Anna, when you're another undergraduate student? The participant had his EEG recorded during the auditory stimuli presentation. So this is the type of, can you hear it? Yes. The type of stimulus that we presented to the participants. This will be a valse or a ternary sequence, right? Then you can identify the symbol 1 that is being erased and substituted by a missing unit, a 0, right? Okay, so Aline also told you about how we define the structure of this sequence and what would be a probabilistic context tree, and for example, for this sequence, the ternary sequence, we have this shape of context tree represented here, and the context tree is always associated with the contingency table. Aline showed you the interest of having deterministic events associated with probabilistic events, and how we can make use of this structure to extract information from the physiological signals. So basically what we did in this paper was to associate those different context trees here represented, for instance, in pink. So you have the electrophysiological signal, the EEG signal here, and the pink would be the symbol 2 preceded by 2 symbols 1, right? And here the symbol 2 preceded by a 1 and a 0. So this will be, as Aline told you, a manner to compare from different branches of the tree, compare statistically these branches of the tree to decide whether or not we keep or prune each of these branches, right? So employing the projective method, it was possible to test statistically each of these branches, and then we came up with this this information, context trees retrieved per electrode and per participant, and we then grouped all this information for each electrode, and we had the mode context tree, and we could then ask whether or not this mode context tree retrieved from the EEG signal was closest or farthest from the original tree, right? So this is another topo plot of the brain here for the ternary sequence. And you can see here that the green spots are the ones where the mode context tree is closest to the original tree. Here for this sequence, we have this frontal electrode and frontal lateral electrode and this temporal electrode, for which it was possible to retrieve the structure of the sequence of auditory stimuli. So at that point, we were very, very happy to show that the context trees generating the sequence of auditory stimuli could be effectively extracted from the EEG signals. And we thought that this was an important step forward to the statistician brain conjecture. Here I want to call your attention to at that time we were also dealing with an important question, which was to be capable of organizing the data and the metadata that we were collecting on all these experiments. And this was possible thanks to the work of Kelly Rosa Bragueto, and together with other members of the NeuroMat team. We created this neuroscience experiment system that allowed us to organize the data, the electrophysiological data and the metadata, so that other people could easily use this data and work in new types of analysis. So this is some publicity on this important step that has been done within NeuroMat. This was the PhD thesis of Fernando Najman. We worked with Marcela Zwark on employing this data set and extracting from triplets of the sequence of auditory stimuli a new statistical approach to identify the regularities and the proximity across the different elements of these sequences. And Marcel is going to talk a little bit more about this pretty soon, so I leave room for her just to tell you that this was done on this context. And also, as a publicity, we did a lot of work to disseminate this this project. So there is a video on YouTube called The Statistician Brain for those who are interested in knowing more about this. Antonio Galvez always said that we had to do the dissemination from the battlefront. So we kept doing these pieces of dissemination while we were recording data and analyzing data. So this is also a point I wanted to make here. Okay, so the other important front of the Statistician Brain project was the development of this game, the goalkeeper game, that required a lot of work of the NeuroMat team here. One of the sessions that we had with colleagues here, André, Maria Elisa, Bruno, discussing on how this video game should be presented and which were the important elements. And we came up with a very nice game, which is available on internet, and which was used to test Parkinson patients, employing deterministic sequences of events, but also together with colleagues from the NeuroMat to test the statistician brain conjecture with this device, right? So here's just a picture of how the goalkeeper looks like. The front page of the goalkeepers looks like. It's in Portuguese, just an idea to with the instructions to the participant, and the participant has to play as a goalkeeper to choose, as Aline said, from where to where the kicker is going to shoot the ball. So here I have just a trial, for a couple of trials for you to see the game. So you are the goalkeeper and you have to guess or to estimate to where the kicker is going to shoot the next ball, right? This is a very good goalkeeper, by the way. Okay, so this was the first paper employing these context trees as kickers in our game. This was done with Nosling, Jesus Garcia, Antonio Galvez, and Marco Gubitoso. I would like to say a special thank to Jesus Garcia, who helped us a lot when Antonio Galvez passed away. So it's a tribute, also a special tribute to him, who gave us a lot of support on the final process of publication of this paper. So here again, just to show you, you have, in this case, a given context tree, and each trial corresponds to a choice that the goalkeeper has to make. The screen appears, he's ready to make a decision, and then these red arrows appear so that the participant has to choose to where the kicker is going to shoot the next ball. And the goalkeeper, importantly, has to take the past sequence of events into consideration so as to predict the outcome of the next one. So it's a learning game, right? So in this work with Hernandes and collaborator, we were interested in comparing some of the context-free properties to try to understand if which context trees were more easier or more difficult to learn, which sequences, stochastic sequences, would be more easier or more difficult to learn. So the first question was, the first manipulation we did was to, for a given context tree, we changed the probability distribution of the context so that to enhance the entropy. So we have the same structure, but two different trees with different entropies. Here is the sequence of symbols or events for the context tree 1, and here for the context tree 2, and a graphic representation of this sequence below. So this was the first question we addressed. And the second question was, does it matter if we break up the periodicity? I'm sorry, it's not very clear here, but for the same two context tree and with the same entropy, what we did was to change again the probability distributions here so as to break up the periodicity of the sequence. So the symbol 2 now was not anymore taken as a reference for the sequence, right? It could change from time to time. So this work was done entirely online. The participants played online. It was during the pandemics. And here is a representation of each of the 4 context trees. We estimated the proportion of correct predictions per window of analysis across time. So we had 6 windows of analysis. So this is the time arrow here. And what we can see is that the context tree 1 is easily learned by most of the participants very early. Each dot corresponds to a participant here. Context tree 2 takes a little bit more time, but eventually all the participants, or most of the participants, are able to learn the sequence. And for context trees 3 and 4, it was clearly more difficult for the participants to learn the sequence. So this is represented here in this ANOVA analysis. It's clear that changing the entropy doesn't affect much the learning, and eventually the two context trees are quite well learned, whereas the difficulty, the number of contexts, and the breaking up the periodicity affected a lot the capacity of the participants to learn the sequence. This is just part of the work that we have done here, just to show you, as Aline also mentioned, it's possible to model the learning of these participants by reconstructing the context trees across time, right? So for context tree 1, 2, 3, and 4, we see that context tree 1 and 2, for these context trees, is very early in the process. It's possible to extract the structure of the context. Whereas for context trees 3 and 4, the mode context tree of the goalkeeper matches that of the kicker from the from the 3 or the 3rd or the 4 window of analysis, right? And we also see a high fluctuation in the proportion of leaves identified in the context tree, suggesting that the participants keep guessing, keep trying to identify the structure of the sequence. So now I want to show you a little bit of work in progress. My collaborators here, and it's also at the poster session, so I invite you to see these results, these beautiful results of the poster session. This was the work done mainly by Paulo Cabral Passos, Priscila Azevedo, and with the collaboration team and led by Aline Duarte, who guided us on the Germanic forest of context trees. So now here what we did was to record the EEG activity of participants while they played the goalkeeper game, right? So this is the tree that was employed in this experiment. It's a simpler context tree, and here is the contingency table. You can see here that we have one change for given context tree 0, the probability of occurrence of context tree 0 for the next symbol is 0, for the symbol 1 is 0.3, and then for the symbol 2 is 0.7. Here we have the sequence of the penalty taker and the response of the goalkeeper while we were recording the EEG scene. So here again we employ the statistical approach, the statistical analysis, as Aline told you before, which was an important contribution from the NeuroMat team to functional data analysis. So we do again here from, if you take each of the events, we are here interested in the period of motor preparation for the next event. So given, for instance, context 311, we are looking at the motor preparation for the next event 0. And we want to compare the EEG activity of this chunk of EEG with the chunk of EEG corresponding to 0, but preceded by the symbols 2, 1, right? So here again, the projective methods. And one interesting innovation here was to calculate the bounding, to employ the bounding distance to estimate the distance between the context tree of the kicker and the one of the goalkeeper. So here we have a matrix that allow us to define a distance between these two trees, starting from the 0, where the context tree of the kicker and the goalkeeper look like the same, to, for this matrix, 2.25, which would correspond to an empty tree, right? So what was done here was to, so this is a topo view of a brain. You have the electrodes from which we recorded the EEG signals from the very beginning of the experiment, when the goalkeeper started doing the experiment until the end of the experiment. We had 1,500 trials here. And what we can see here is the scale for the bounding distance from closest, so bluest is closest, when the distance between the goalkeeper and the kicker is closest, whereas for the farthest distance will be around the yellow colors, right? So you can see here, this is the qualitative data just to give you a glimpse of the evolution, the time evolution of this, the learning process, right? And, here we have the success rate, the mean success rate for all the participants, and Paulo had this nice idea to correlate the bounding distance with success rates for each of the electrodes. And what was found here was that there was an inverse relationship between success rates and bounding distance. The higher the success rates, the shorter the distance between the goalkeeper and the kicker. And this holds for a number of electrodes, but not for all the electrodes. So this is depicted here in this topological view of the relevant electrodes, and with the correlation, the significantly correlated numbers here. So, and the highest correlation was found for the parietal electrode P3. Okay, so this is an interesting step forward the statistician conjecture, where now we are correlating the learning process as inferred by the context tree and the performance, right? Where the highest performance associates with the closest similarity of the goalkeepers and the keepers context tree. Well, another work that we have done employing the goalkeeper game was to measure response time. So this was part of Paulo Passos' PhD. And here we employed, this is the representation of the context tree here and the sequence of the penalty taker or the kicker or penalty taker and the responses emitted by the goalkeeper. So we noticed at some point that the response times differed as a function of the good or bad choice made in the previous event, right? So I invite you to take a look at this very nice manuscript. But the conclusion of this paper is that response times are modulated both by the context and the result of the previous choice. And this inspired us, this result inspired us to look at the cortical spinal activity during the goalkeeper game. So this is work led by Victor Moraes, his PhD thesis, and also supervised by Bia Ramalho and our team, and Jesus Garcia here again with his wonderful helping hand. And here, just to show you the idea here, we applied single pulse transcranial magnetic stimulation during motor preparation over the motor cortex. So the participant is playing the game, and while he plays the game, during the preparation phase, we apply a TMS pulse, and we also measure the response time. And the key question here is how much of the feedback result, whether he has made a good or a bad choice, whether and how it affects the motor preparation for the next event, right? So this is the experimental setup. The coil is placed in the scalp, and we measure basically the response from two hand flexor muscles, one which is an intrinsic flexor muscle, the FDI, and the extrinsic flexor muscle. Here is the description of the context tree that has been employed in this paradigm. So we worked with blocks. So we'll have some blocks with TMS and other blocks without TMS. This is the success rate across the several blocks, and you can see that the participants are able to learn the task. And we then analyze it, how much? Analyze the response times. So we did applied the linear mixed model, where we are testing the effects of block versus predictability and error. And as you can see, the response times reduced from block 2, or the first block with TMS, to block 6. And we separated the context into predictable and unpredictable contexts. And what we found here is that the unpredictable contexts were related to larger response times, as expected, right? And for the cortical spinal activity, we got a very interesting result. And so again, in the same model, we have we separated the results in terms of blocks, again with the linear mixed model with block and predictability versus error. And what we find here for the extrinsic hand muscle is that there is an enhancement of the map response from block 2 to block 6, so an effect of learning the task. And again here, we have lower map responses for predictable whenever the event was predictable as compared to unpredictable. So this is somehow the inverse response as we found here for the response times, right? So the response times are lower, and there is this predictability effect across time, and the cortical spinal excitability is higher from the first to the, or from the second to the sixth block, an effect of learning, and with the unpredictable responses being higher. More surprisingly, and we were very excited by this result, when you look at the FDI, which is the effector muscle, which relates to the choice of to pressing the button choice, we see that there is an interaction between block and the success or failure in the previous event and predictability. So as if this hand muscle at the third block, when the participant has learned the sequence, acts as a readout, has a readout of the whole pattern, the sequence pattern, right? I'm sorry, I'm going very fast. So we have this cartoon showing these effects of predictability and the fact that the participant has done has made a correct or bad response in the previous trial. And I invite you to see the poster, because then you can discuss with the students and clarify any other question. This was a beautiful event. We had this opportunity to be together in the Institut Henri Poincaré, so just to as a reminder of the beauty of this project and the nice experience that we had together. And now an acknowledgement for the funding agency. Thank you.
Do we have questions? Quick question. We need it because we are in YouTube.
Okay, so I'm not that loud. Thank you for your presentation, very nice work. About the TMS study, when did you give the TMS pulse? At the onset, or how did you know the preparation time? So usually when we do such paradigms, we give it on specific time to have the maximum effect.
Yes, we did it at 400 milliseconds before sorry. So you have here the person is responding here, right? Yes. And we have this preparation phase. So we gave the TMS pulse at 400 milliseconds in the beginning of the preparation phase, in fact.
So it's zero.
Zero.
At zero time.
Yes.
Did you try the other times?
No, we didn't. Well, you know very well when you work with TMS, you have to make choices, right? And we prefer to have a sufficient number of pulses, because this was done 600 times, and we wanted to see the effect of learning throughout time.
But there is, for sure, there is an optimal time.
Yes, then this is another experiment.
Course, yes. Yes. So of course we need to have either general times like at 0, 200, 400, let's say.
Yes, yes.
Or then you need to optimize to personalize, which is a bit more difficult.
Much more, yes. In the literature, we have this period of motor preparation that spans from 600 milliseconds to the moment you press the button. So, yes, but you're right. We could try other spots,
And one
fine
more,
spots.
because these are very important. I have also some relevant things, but I wasn't intending to show tomorrow, but I can add them, or I can show you outside that. Did you try to use, instead of TMS, RTMS? Like instead of giving, so, and then you can give it at 50 Hertz, which would be fast and narrow, so then you would be more specific to the movement, but you could give it also with 5 Hertz, so that in order to impair cognition.
Yeah, you want to interfere with the task, right?
Yes.
Yeah, we just, in this experiment, we wanted to probe the cortical spinal stability at this moment as a tool to infer about the learning process. You see, this is why we are so excited by the results on the FDI, where you can really see the effect of having had a good or bad response in the previous event, and how it affects and also associates with the predictable and unpredictable context. But yes.
We have variable results though, because when you repeat one, you can suppress and impair one muscle, one cognition of the muscle, but you can also facilitate something else. So this would be very important general information.
Yes, thank you.
So
I'll think about it.
Yeah.
Yes, very nice. Thank you very much.
Other comments or questions? So let's thank Claudia again.
Thank you.
Vocês viram a mudança
Não, dessa não. Nem vi lá, olha que dá.
Não, a Cláudia quer
Você é a chair, ó, acabaram de mudar, não vai ter um intervalo, a gente vai fazer direto, eu vou depois do Marcelo. Daí a gente diminui.
So we'll continue with Andre's talk after Marcella's talk. Okay, and complement will be afterwards.
Oh.
You gain,
Think it's
you
more
can gain 20
rational.
minutes.
Yeah, so you carry on with Andres.
I can try to. No, it doesn't matter, Claudia. Come on. No.
What is your presentation? This one? Applied perspective?
No, not that one. No, not that one. It was a. Usually it's to me, no?
Yes. Maybe this one?
No, this is not in.
This one.
Okay, so our next speaker is Marcella Svark, our collaborator from Universidad Sant Andrés. Thank you very much, Marcella, for joining us here today.
Well, hello everybody. Thank you very much to Antonio and Claudia for having invited me. Well, I first started working with Antonio Galvez for the very first time back in 2005 or 6, something like that, where the projective methods were not even yet published, but I was working also with Ricardo Feynman. And so we applied the projective method, but to linguistic data. And then I didn't work anymore with Antonio until it was like during the pandemic in 2020 that Claudia and Fernando were trying to apply in a pre-processing stage a procedure in a paper that we had developed like 10 years later, or 5 years later, early with Ricardo. And there was a tuning constant that it wasn't working properly when they tried to use it. So Antonio guessed that that part of the tuning constant was more related than Ricardo. So he sent me an email and said, in this paper, this is not working properly. Can we talk a little bit? And I said, okay, yes. And he sent me a Meet link and said, can you join me now? And it was pandemic, so well, I just entered. And well, we talk a little bit about that constant. I know it. I knew that it could happen, that it was really subtle to tune that constant. But he started telling me about this project that you were starting to working with, and well, here I am. I joined you, and it was like a really nice way of starting and a really nice trip through all this time. So I'm really glad. So well, the idea is, Claudia showed some results, and the idea is to unveil a little bit math beyond that, just a little bit. So well, as I said, this is a joint work with Antonio, Claudia, and Fernando. And the motivation comes from the data that Lini and Claudia described, the hand clap experimental procedure. By that time, they were finishing this work, where the work of Hernandez et al., where they could retrieve the context tree that generated the data. So our idea was to identify if there were some classes, of models used by the brain to encode statistical regularity of the environment. That was like the general goal. And our question, was if we could retrieve this generality from the EEG segments. So the signal was generated for the hand claps was a sequence of stimuli, and then you get the EEG, and if we could retrieve it. But the idea was to retrieve it in the most simple way. What could we do about that? It was the most simple structure that we could identify, not telling anything to the data. So well, here is the data. We used the quaternary sequence. So it was a strong hand clap that is represented by a 2, then a weak hand clap represented by a 1, then a silent unit, and then finally another weak hand clap. And that repeated. But as Alini said, they added stochasticity to this, so the weak hand claps were replaced with low probability by a 0. That means a silent unit. So the idea is that now that we have sequences that are different, if we can replace this basic structure. So well, when you don't want to tell anything to a problem, a good way to analyze this by cluster analysis, because basically when you do cluster analysis, what you ask your data is if there is something going on there. If there are groups, but you don't know anything. You don't know if there are groups, how many groups, if they are conformed in an unbalanced way or not. So it's like the best way to ask data, what do they look, without telling them anything at all. So what we propose is a clustering procedure for this kind of data, and the procedure has 2 phases. On the first stage, we deal in an individual level. This means that for each participant, there were 10 participants. For each participant, you have a lot of electrodes that were measured when the signal was stimulated. And you first need to cluster data on each participant. You have a clustering procedure for each participant. Then what you need is to merge all this information, join it in a certain way. At the beginning of the process, we didn't know how to do that. And we are going to employ a consensus clustering strategy. So first of all, I'm going to talk about the first stage, the individual stage, when we are going to cluster data for each participant. Well, the conjecture that we have, this minimal structure that we were looking for, is that the strong bit was the one that was ruling all the learning made by. So basically, if we consider since the data came from this context tree, so we knew that, and this regularity between every 4 stimuli, so we knew that the length of the path that we had to look was 3 times 3 hand claps or not, or silence or whatever.
So we knew that if that was going on, if the strong bit was the one that was determining the structure, then the ideal cluster was one cluster that had this conformation. One cluster was the one that has the strong in the last position, another one that has a strong bit in the middle position, this one, the blue one, that has a strong bit in the first position, and the other one that doesn't have the strong bit, what comes after the strong bit. Well, so the idea is, this is what we want to do. We don't know if we are going to be able, but that was our goal. Well, so basically, what we have done is, these one are the hand claps. The person is listening at them and it's being recorded. Here you have the EEGs. Here are those contexts, because following the notation of context 3 are these strings of 3 stimuli. So each time one of those strings appear, you cut the chunk of EEG and you put them together. So what you've got are, for each of these stimuli, you have a family, or you have a set of chunks of EEG which are functional data. So our idea is to, well, considering that Antonio liked a lot the projective method and liked a lot this way of seeing if two sets of functions have the same distribution, test all the possible pairs of distributions, see which one of them were the same, and based on that, construct a clustering procedure. So how did we do it? Well, we have these sets that are YU and YB, and we want to know if YU and YB are the sets of chunks of EEG data generated under the same context, under context U or under context B. And we want to see if they come from the same distribution, QU or QB. So the idea is to consider a distance between QU and QB distributions, and then put them on this dissimilarity matrix and do a clustering procedure. So here appears where the paper where Cuesta Alberto and Freiman proposed this goodness of fit test for general data. Specifically can be applied for functional data. So we consider the strings of symbols, and then we have the sets of, this is the mathematical idea of the picture, and we have the sets of chunks of strings that would be the Ys. And what we want to test is if the law of both sets is the same. So what we do is, well, we will generate random directions, project the data of the random directions, and once we have done that, we have univariate data. So we have these sets that have the data projected on direction B, and then we can test if those sets have the same direction, for instance, via Kolmogorov and Smirnov test. So this is the idea. You have the sets, you project them, you have the cumulative function distribution, and Kolmogorov-Smirnov measures the maximum distance, and if it's big, you say they are different, and if it is small, they are. Well, that distance, we call it D, and it is well known when you work with the random directions that in spite of being a theorem that says that if you choose just one direction at random and you see that the projections are different, the distributions are different, that's what Cuesta Alberto's Freiman proved. It is well known that if you do it just once, it's not stable. In fact, they also say it in the first paper. They write it's not something that we discovered. So the idea is that you have to do this procedure several times, and there are basically two ways to tackle the problem, to decide and to construct the test. And these two alternatives are, on one hand, to consider the distance, given the Kolmogorov Smirnov distance, and do an average over all the random directions that you have done. And the other thing you can do is you take the distance, you see if the distance are bigger than a certain threshold given by the asymptotic distribution of these statistics to guarantee that it has level, the wanted level of the test. And then you just count the number of times where you reject the test, and what you average is this result. No? In the literature, you can find that this test is applied in both sense. So first we decided to apply it in this way. So basically what we have done is we chose a random direction, we projected all our data on that direction, and then did all the Kolmogorov-Smirnov tests and construct a matrix that had a 1 when you rejected and a 0 otherwise. And this matrix has been built many times, and on the n direction. Once you have all these matrices, what you do is you average them. No? And now here you have a dissimilarity matrix. Once you have a dissimilarity matrix, you can immediately apply any kind of but a lot of clustering procedures and see what happens to your data. In our case, we decided to apply a complete linkage procedure. So we are comparing empirical distribution sets of functions. We are considering one-dimensional projections of the sets, but what we are not doing is considering the distance between individual functions. Many times when you are dealing with functional data, what you want to work directly with this, and we're not doing that. We're working with this data formula set. So when we come to the data, well, we consider the same data that Alini and Claudia talked before, and we consider just some of the electrodes. So we knew that we had learned from Hernandez et al. That the main information was in the prefrontal region. So we consider electrodes from the prefrontal, right and left prefrontal region, and as a control, we use electrodes from the occipital region. We had a preprocessing of the data, trimming 10% of the outlying observations. This is because I wasn't able to, we used Feynman Muniz because I wasn't able to tune that constant of the paper I had with Ricardo. So I suggested to switch to another way of trimming the outliers. And what we have done is we average the signals of 3 electrodes from each of those regions. So these are the electrodes that we consider and that were averaged for this analysis. Well, but by this time, what we had were for each participant, we had each region, we had 18, we had a clustering structure, no? So now that we have the 18 clusters, we have to summarize them somehow. So do that for each electron. So now what we are going to speak about is about the way to summarize these things. So what we consider is a consensus clustering strategy, where what we have done is it was to combine the results of all the participants. So the idea is that we have all the, for instance, the prefrontal, left prefrontal region, we have all the dendrograms that give a partition, and then we construct a matrix that each time what we have is the number of times that the context, this one has 12 for 12, because there are 12 contexts. For each context, the number of times that they are clustered together, or we average them, so it's the average of times that they are clustered together. So then again, we have sort of a dissimilarity matrix, and we can again apply a clustering procedure. So we apply this clustering procedure, and we obtain the final results. the final consensus cluster. No? So it's like a cluster of clusters, we call it. At the beginning, we called it cluster of clusters. So we learned that this had a name. Well, so these are the clusters that we have found. I think there are I don't know if you get to see the numbers, but the first thing that we can see is that in all the cases there are 4 clusters, which was the same clusters that we had identified in our model. And then if you get to see the numbers here, well, we have a really good site. But what you can see is that in neither of these cases we can retrieve the exact partition. So we measured how far away we were from the exact partition, and we found that in the prefrontal regions we were close, but we weren't close on the occipital region, which was the control. And then, of course, we need a robustness way to measuring if these results were by chance or not, in the same way that Aline said. So what we have done is generated matrices of the similarity, like the one, like this one, let's say, and say, well, if just it would be randomness, how common would have been to observe this kind of dendrograms, of partitions. And what we've got is that for the prefrontal region, the odds were very, very small, while in the occipital region, the odds were high. So we guess that we are finding, our finding is that we are retrieving that basic structure. Well, that was Fernando's PhD main result. But when we went through this journey, we had to take many decisions, and there were several questions that remained unanswered, some theoretical questions, basically. So the first thing is that we were using asymptotic results. When we were using the cohort of Smirnov depths, we were using asymptotic results. But our sample size weren't that big. So, or some of them were big, and another weren't that big. So it would have been great instead of having asymptotic results, we have any kind of results for finite M. Then another question was, well, we decided in a certain way, in an arbitrary certain way, how many random directions we take. But can we say something about this? And then we decided to generate the random directions, well, following a Gaussian process, but the way in which we chose that process, again, was, well, we decided to do it with Brownian bridges, but is there a way that's better for choosing this distribution? So this question is specific of this problem, but there are many procedures based on random directions, and these 2 questions are common to all the procedures that belong to random directions. So what we decided was to continue working. So first we decided to tackle these 2 problems, and the cornerstone of our procedure was the hypothesis test, and we are going to consider the average of the distance after projecting in a univariate way, and the populational counterpart of this would be this. That would be the so basically what we got is a bound error rate for the theoretical distance to the empirical distance that depends on n and depends on m, and our exponential bound depends both on n and on m. So we have a result and know how to choose it and how do they affect the procedure. And it's a neat bound. This bound yields a critical point for the statistics that is sharp. And moreover, we have also an exponential bound for retrieving the good partition. So there are a lot of things that we can say, because now we can say that we can retrieve the partition without choosing how to cut the dendrogram. This procedure cuts the dendrogram by 2, so it's kind of a lot. These bounds are neat and are nice, but have one problem, that we made the proofs with Heffding's inequality, and Heffding inequality, it's a very rough bounds, very, very rough. And what we observed in data was that the variance of our statistics was very, very small in comparison to the to the rough bound given by Heffding. So we decided that we had to use that information to have get a better bound, and that's what Bernstein does. It's a way to refine this bound. But of course, that variance is unknown, so we had to estimate it. So we needed to use an empirical version of Bernstein's inequality, and we did it, and we obtained better bound. But of course, it's off because it's not implicit. So this one is better. I just for you to know that it's off. That's all the point is the offness. So it's better, but in order to compute this, you need an algorithm. But well, we did an algorithm, so that wasn't a problem. And here, just to show that we can do it. And again, we have now a better bound for the probability of retrieving the correct partition. But, well, this didn't work out properly on our data. Unfortunately, the data was inspiration, but sometimes what you do doesn't improve your empirical results. But we tested on 2 synthetic data sets that we generated. One of them is a theta scale Brownian bridge. So what we have is we choose 3 different values for this theta. 2 times we choose the same, 3 times we choose the same, and another time we choose the same. So we have 7 sets, and we should cluster these 2 together, these 3 together, and these together. We chose different values for the level of the test, and for the number of the random directions, and for the number of directions, and for the sample size, and we did 500 replicates. And then we had an autoregressive model, where again we have this parameter that was again chosen in 3 different ways. And in these cases, what we get is that the proportion of times that we retrieve the good partition increases as the sample size increases, and the number of random directions doesn't seem to be it's not very sensitive to the number of the random directions. This is for both cases. This case is a little bit easier. Then what we did is, well, we compared, there's a measure that is useful to know if 2 partitions are similar. It is called adjusted rand index. We studied the adjusted rand index over all the situations, or over all the scenarios for both procedures. And in both cases, rapidly goes to 1, and 1 is the best thing. So that it's another way of showing that we're retrieving the good partition. And here what we've got is the error, we quantify the errors that we can have an error because we put the same, we assign data sets with the same law to different clusters, or data set with different law to the same cluster. And this error, we almost never do it, and this error is the one that is harder to detect. But basically, it works well. And what remains to be answered is what about the choice of the direction in which we have to project? And Fernando are working on this right now, so I hope that we can say something soon. And well, the results appear in these two papers. One is the one that Claudia said, and this one also. And so, well,
Thank you very much, Marcela. Questions? Questions? Okay, Marcela, thank you. Thank you again. We can maybe discuss later. André, please.
As we change the shadow, and when start the I first want to thanks to Claudia and Rocky for the invitation, and we was discussing in the lunch how many times we start that, and probably we found an email from October of 2011, something like that. That make also 15 years with work. 2 years before the start of the official start of NeuroMat. And what you present is some applied perspectives, some that we did before and some that we are working now, some that we are trying to send the paper this week. And the idea, someone asked about how deep we can understand the way that this kind of inference, statistical inference, could be found in the brain. And when we think about the idea of the brain that operates on a probabilistic, as a probabilistic machine, that's something, the way to say about what's the statistical brain conjecture. Probably we are talking, and I am a biologist, and if I apply that on a biological perspective, probably we can find the idea that when you think about the statistical inference, we are trying to change the way to see how we or any organism interact with the environment. Normally, we like to think the idea of a stimulus and response, and and that's a very important way to interact with the environment. But when we talk about the anticipation, we are looking for another way to interact with the environment. That is, you can make some anticipation of stimulus occurrence to make your response better, and that could be very important. And obviously, when we think like that, we need to accept that the brain is not the only way to make inference or to make statistics. Probably any organism needs to do that to be better adapted for the environment. And that's a strong idea for me also. And I think that when you look for that, we need to organize the idea of where we are talking about and where the brain is especially important. If we think we can make anticipations for a very common, like day and night patterns that are temporal, that follow temporal regularities. And we also have the predictable patterns that we can learn looking for the past or based on the past. And obviously we have the unpredictable patterns. If we think about the stimulus response, it's this kind of pattern. But we look for the most challenge ones, that is the one that could be predictable, but you need to learn how that will be predictable based on the past. And you need to find the rule to make the model. Probably the brain is the most important for that. The temporal one, we have in biology another kind of machinery or way to solve this kind of regular aspects. that we call in the area of chronobiology, things like that. But probably we are talking about that, and that's very important. I will pass very fast the presentation because we have a time. But I'm trying to organize this idea of the temporal regular ones, learn contingencies, it is the stochastic fluctuation that it's not possible to predict, in a sense that would be very, in a physiological way, very compatible with the way that we think about that. That is, when you think about the learning contingencies, basically what we are talking is that based on the past experience, the brain intensifies causal patterns, building internal model to predict specific outcomes based on the past environmental contingencies. That in the idea, and that's what we normally work here. And we put that on the idea of Claude Bernard, that is a very important person in physiology and biology, that proposed this idea of the milieu intérieur, that you have this kind of organization to define life. Probably we can think on this idea of Claude Bernard perspective, that the predictive maintenance is exactly what you need to make the set point, the definition of the set point, where we are put the idea of the internal, the milieu intérieur, or the internal organism works. That's for me very interesting, because when you think about that, the question is about how deep is in the brain. It's not on the brain, it's how deep is in the life organism, or in all the organisms. Predicted the environment, how that something important will occur on the environment, is a basic aspect of any organism. And maybe the point is how complex could be the information or the model that you construct in the brain. And that's I think is the point. That is, along the evolution of the organisms, the brain is probably the solution that can produce the better or the most complex models that we will be used. You asked the question. And that makes sense for you on this perspective. That is, I think the brain is probably the best way to find very complex model, but it's not the only way that, or the only place where you find this kind of way to interact with the environment. I know you can ask now. I will pass very fast if it's necessary. Let me think.
Yeah, that's something that I think a lot about how deep, louder. That's something that I think a lot about how deep it's embedded with, like, is it neurons? Is it a conjunction of neurons? It's the brain, it's the muscle. But then you said the brain may be the most efficient machine that finds the solutions. But how can we test if we don't know? That's something that I think, like, how complex can we go? And how can we produce stimuli that passes through the most known circuits that are related to cognitive process? So how can we bypass this and test how deep is this learning process?
Yeah, there are a lot of questions in that.
Yeah. So
there is probably this is what we are trying to do here, or to say and to understand the models. But maybe you can change the platform using the analogy of the machine, and ask for different systems, maybe in the colonies of the ants, or for other animals, and to understand that's a part of the And the first thing that we did about that is how to try to understand the way that the complexity is present and the way that we understand that. We did an experiment that is from 2016 and revisited by Claudia, as she told us. And about the complexity here, we use the entropy and the second order entropy. It's difficult to use entropy because you need to define the order that we use to calculate. And what we found that is you have this kind of, when this is blocks of training, then you have the curves of learning, and that's the complexity. And then you see that the reaction time is better in the low complexity, and when you increase the complexity, you have this kind of change in the performance. And in some moments, all the complexity turns into described by the sigmoid model in a very difficult to say. That's when we look for that. That's a paper from the NeuroMat also. We look for the necessity to describe that in a better way. That's why entropy is not so good. You need to define in a prior sense the order. That's a problem when you look for. But that shows that we can really, the idea that the complexity is the point, and in some way we need to discuss with that, emerged for us from this kind of experiments. Obviously, when I will put that on, there are a lot of texts I will explain. When you looked for that, one of the ideas that we had is, if the brain make models, how they can control the use of these models, since the environment could be respond in a different way than the model predict. And then we've made an experiment. This is the data was published this year in Brain Science. This data, not exactly in this sense, but this data was published in January of 2026. And we did was two different ways to measure it. And all the data that I will present is this kind of serial reaction time task. That is the same that Cohen showed for us in was the piano learning. And we used for sequence the structure that was intermediated difficult when was measured in other paper. I don't remember the name of the author, the students of Galvis, who measure a lot of different. He is in Natal now. Bruno. We take one was the intermediate, not so difficult, not so easy, and we isolated each one of the events. Then we have in this condition the events that are fixed. That is the same, presenting the same position, in the order where you have the possibility to came to two other, come to 2 or 3, and we can see 1, 2, and then we have this 1, 2, and then you come to 2 and 3 with different probabilities, 25 and 55. And in 2 different conditions. One was the realization, the actual realization of the task, and the other one was an imagery one. And when we see, comparing both, we can look for the reaction time here, not for the accuracy, but for the reaction time. That is when you look for the one that is less common, that is the V2. They are the time to answer for this one is lower than in the simulation, the mental simulation, than in the actual execution. And that show for us that probably we can think about the idea that the brain, when they don't realize, they only imagine the idea, you have this aspect that is, you are more similar on the execution about the model of probabilities. That is, you have the 100% of chance to occur, 55, they are very similar, and the 25 is different for the others. When in the actual realization of the execution, the motor execution of the sequence, you have this kind of the problem of you need to correct each one of the times that you make an error. You don't have errors here because it's not possible to be error, it's only measurement. But here you need to correct that, and that's important. Taking these two examples, that is, complexity is important, and how we predict depend about the possibility to access the information there. And in fact, the brain look like to use this kind of information to make this inference that will be responsible for a good or a bad response. We apply that in two different clinical perspectives. One, Claudia mentioned it, that is in Parkinson's disease. And we use for that a presentation that will guide the kicker, and the person need to play as the goalkeeper. And we did that with people with Parkinson's disease. And the idea here was, if in Parkinson you have this problem of automatization, since the dopaminergic problem involves a disruption of the systems of produce automatic answers, we compare the performance here on the goalkeeper game with two different aspects. One was a part of MoCA, that is a very important, the standard code to define the progression of disease. And the second one was the quality of gait. And what we find is that then what we did is that they played the game, we applied the measures of MoCA and the goalkeeper, and we compare with gait performance. And what we find is that more information is possible to infer what's the point in the progression of the disease, or in the gait, the loss of gait performance, looking for the goalkeeper game, then looking for MoCA. That was very interesting because probably we can use this kind of approach, that is, use the inference, the quality of the inference, to see the progression of the disease. The second one is in clinical schizophrenia. That's the paper that we are trying to send on the Friday. That makes 2 months that we are trying to send on the Friday, and the Friday never arrives. And it's exactly the same sequence that we used in the other one, in the imagery one. And we compare the performance reaction time here in schizophrenia and control groups, using imagery and real conditions, real and imagery. And one of the interesting aspects, that is when we compare the PANSS, the part G of the PANSS, there is a classification of compromission of positive and negative syndrome scale, and with the performance that we measure for each one of the patients, we can see a correlation, specifically on the real, not imagery, but a negative correlation that could be show something interesting on looking for the disease. Also, it's not progression, because it's not a perspective of progression, but it's how complicated is the disease, considering the here also a gold standard, that is the PANSS. Taking those two together, we think it's a good way to think. Maybe this first assumption that I did, that is maybe more than only a superficial way to look for the brain. Look for the capacity to make inference is a very powerful way to look for an important aspect for the brain. That is the capacity to make this inference, to create models, and to make models in challenging conditions. Also for these two approaches that we did. The other one that I will show, it's something that we are doing now. That's the work of Fernanda that will be presented on the poster session. That is, we are trying to make this a project that we make part of the fatigometry, and we create the project in collaboration with different associations of aeronauts, that is the pilots and the people of cabin, and also with CENIPA, CNPA, and CNFH. There we are the government structure associated with aeronaut to control accidents on flights in Brazil. And what we did that, the idea is to estimate fatigue in Brazil, Brazilian civil aviation system, and proposal of strategy for its mitigation. What we are interested here is try to use this kind of capacity to make the inference, the correct or the good inference on some perspective related with fatigue. This is the data that we collected, and then we can see it's not exactly, but we can see that both KSS and fatigue, that is the Karolinska scale and Samparelli scale, there are two subjective scales to measure fatigue, and we can see that during the day that the subjective perspective enhanced for the groups that we measure, and that's something related with the subject perception. But we know that when we see for the performance in attention tasks, that's not so good, but here is 10, is 4 a.m. Probably day is here, and you have a better performance during the afternoon. It's not possible to see here because the size, but the better performance of in this kind of task normally is found in something in the middle of the afternoon during the daytime. And we are trying to see for the gold standard way to measure use it to measure fatigue, and compare that for the performance in some structure that we applied. When we first use psychomotor vigilance task test, that is a gold standard to measure fatigue or to estimate fatigue, and a very simple, the PVT, the psychomotor vigilance task, it's a very simple task that is a simple reaction time task. That is something appears and need to press boot. You measure the time. That's kind of, you have in the monitor, not possible to change the color, and then you need to press the button, and here you will see your performance. That's what exactly happening on the PVT task. We applied that for 35 subjects, and what we see, this is only the performance considering the age, is the why we used the first block as a training, and the other four for the blocks, for the 4 blocks for test. And here is the performance. The 4 blocks we found some interesting aspects, the difference between men and women. This is only the reaction time. If we look for the number of errors is inverted, the man go faster, but they make more errors, and the woman go a little bit, 20 milliseconds slow, but make a better accuracy on the task. But what we are very interested to see is if we look for the moments during the day, that is for these 3 moments of the day, we are not able to see difference statistically, to see difference between the performance. That is, although the fact that this is the gold standard way to make the inference, we are not able to find the difference. Then what we did was use 3 different sequence structures, and that's one, that's the other one, is a fixed one. And we are interested to see if it's possible to see there. This is the results on the sequence. We have a random blocks only to know what's happening in the performance, the motor performance. And I will show only some data about that. The first aspect is that here we have all the subject, the 33, and here we separated in the phase during the day, morning, afternoon, and night. And what we see, we can see when you use this kind of approach, we can see what's not able to be observed on the PVT, the gold standard. And more, when we look for the way for a specific one, and here we choose this one because it's very similar for some aspect that we discussed here before. When you look for this transition specifically, that is the transition from C to A or B with 0.8 and 0.2 of probability of accuracy of each one, what we can see is they make a very interesting separation of the performance. The 80%, you can see that they make better, and he go worse. Or training make a low performance, because you need to make a strategy to solve the problem, to have both possibilities, and this one is very common and this other no. Then what we are interested in, and we did that, and we can see the difference on ERP. It's possible to make an EEG. And what we are trying to do in this moment is to make an effort to create an index that will be possible to measure in objective way this kind of strategy as a way to look for the fatigue. Maybe in the fatigue conditions, they are not able to make a better solution for this kind of duality, that you need to be better, you need to be worst and better in each possibility of occurrence. That's what we are doing exactly in this moment. Exactly in this moment real. We are doing that. And we are trying to apply that. This kind of approach make a possibility that we construct a project, a PP project, that is, it's not only that, but a project to develop a biomathematical modeling software and fatigue risk that's proven on FAPESP. We are working with that. The name of the company that was created for that, safety and optimized standards. Today we have cooperation with different aviation companies, private aviation companies, and with the AGIA system of the Militar Police of São Paulo, and we are collecting data for this kind of approach. Thank you, everyone. That's my final slide, and especially for the people for NeuroMat, that was very important to make all these studies be able, and specifically here to Patricia, that make the PhD inside the NeuroMat, to Paulo Passos that is here, that's very important to all the work. It happened Yanino Scati, who collect the data from the Parkinson and schizophrenia patients, Fernanda that's here, and Rodrigo Pavão that was a student, now is a professor in University Federal of ABC, the ABC University. Thank you.
Very much, Andrea. Very nice talk. Questions? Questions?
Okay.
I have a question. We were talking with Daniel about the effect of variability when we are collecting data. And one thing that we noticed in my team employing these stochastic sequences is that the tolerance to the imprevisibility is very variable across subjects, right? So when you talk, we mentioned fatigue, and how much you think these two variables are mixed together. I mean, if you are more intolerant, you tire faster when you have this type of protocol.
Yeah.
I'd like to have your thought.
No, that's one of the questions that we are trying to answer. We have at this moment on the project, we collect the data from subjects that are exposed for a normal fatigue. On the second semester, you collect from the aeronauts that flight for 2 nights on the morning. And then what we are trying to do is to avoid this kind of problem. That is, anyone will be fatigued. There are no one that can pass 2 nights flying and then be okay on the other day at morning. But what we found when we are analyzing the data is different persons are very different on the experiments. Let me show something that is very complicated. If we see this person have this group, this sequence, or this structure, have no learning curve. And that was a problem for us. Why it's possible to have no. That what did was separate the ones that have the curve and the ones that have no. And what we found is the person that have no curve and the people that have a learning curve are very interested in looking for these strategies. That is what happened with these strategies, and so fast they can be able to do that. And I agree, it's very deep. I have no single answer for that. But that's a point that we can find here, and it's difficult to understand.
We find the continuation together.
Yeah, we start when we ask about that, we start with the idea that there's someone that don't learning. But it's not true.
Thank you very much.
Thank you.
So I'd like to thank everybody and especially the speakers for the session today. And now we are going to the coffee break and then to the poster session, right? Thank you.